Good evening, y'all. Welcome back to another Sunday night electronics bash here on the internet, I suppose. You know me, I'm Jeff Glass. It's good to see you all again on this lovely Sunday night. Hey, Chris, how are ya? Chris, happy birthday! I don't think that's doxing. I think it's just a happy thing. I hope you had a really exciting and good birthday day. I hope you did not get together with too many people, because that's just not the thing we do nowadays. But I hope it was good nonetheless. As always, we'll give people just a few minutes to join us here before we dive in to talking about printed circuit boards. I think it'll be a fun thing to do tonight. As I shared with some of you on the internet out there, I had originally intended to talk about these little wireless modules. Actually, and a couple others. These ones are a basic 433 megahertz transmit and receive pair, and another RFM69 radio module that I have in stock that are really easy to use and really easy to do like wireless signaling and wireless triggering with. And honestly, like this week just got away from me. It's been a bit of a hectic week and an emotional one. So rather than try and slam in those demos in like the past 48 hours, I thought we would sort of take a little diversion, talk about printed circuit boards, and that would be a nice thing to sort of do something a little bit more digital, so I can do the wireless signaling demo a little bit more right. I think will be a lot of fun. But yeah, I think we'll have a good old time tonight. Talking about boards, talking about fabrication, talking about PCB design. I think it'll be great. Hopefully the audio is a little bit better this week. Hi, Palmer. Perfect time. I was just saying I'm hoping the audio is better. You can see my classy new boom mic setup here, which I think is a little bit plosive-y, but hopefully it doesn't seem to be clipping as much unless I get really excited. It's not a great boom setup. It's a little bit. So there's no gain adjustment on the mic pack itself, so the gain structure I think is a little bit strange. But that's all right. That's just what it is. That's what when you pay for like a relatively inexpensive wireless mic pack that came with like a boom mic and a lav. So I'm kind of doing my Justin Timberlake impression tonight. Restrain your enthusiasm. Yeah, for sure. I will definitely not get excited about circuit boards at any point this evening. I guarantee. Speaking of getting excited, tonight I am drinking Snick 3 from Beguile. Wow, there's all kinds of glare. There's no way. Can you see it maybe in this camera? Yeah, the Snick 3 Norwegian farmhouse ale from Beguile Brewing Company here in Chicago. Yes, this is a crowler. This is 32 ounces of beer. It's like half a growler. It's a growler in a can. I am not drinking this entire thing. I'm splitting this crowler with my wife. So don't worry. It's not going to be another loopy-doopy night. Or if it is, it's not the fault of the beer. But no, we've put it in these little, lovely glasses that we had as favors for our parties at our wedding last year. J&M 41419, which I think are really pretty. So it won't be too goofy of a night, I hope. Or maybe it will. I can't really promise anything these days. Snick 3, just so good. Interesting night with the crowler. Yeah, it's thankfully there's a little bit left in here, so at some point I'll do a little bit of a top off. But no, it's not gonna be a full crowler night. We're not going that wild on circuit boards. But speaking of wilding out on circuit boards, shall we just get started? We'll just do the thing. It's gonna be great. Of course, it's a fairly digital evening, but what I've basically done is pulled out a bunch of circuit boards, both ones that I've made and like circuit boards from various products. So as we reference features and things on circuit boards, I'm hoping to have physical examples of most of the things we talk about to be like, and this is what it looks like when you do X, Y, and Z. Partly when we get to the end of our process tonight, we're going to be designing a circuit board together, really laying out a circuit board together. And I picked a board, basically a project that I had done in the past, so that we can sort of do a little time warp where we are designing a circuit board on the computer, and then we also can sort of see and then through the magic of having already bought it, it turns out like this, which I think will be kind of a useful thing for us to do, to have those two things sort of next to each other. So yeah, let's just dive in to talking about circuit boards. Things we're going to talk about today: what the heck is a printed circuit board? We talked about this a little bit last week on our talk about soldering. The parts and pieces and features on a circuit board, how you get one manufactured. We're going to talk about schematic capture, which is how you get the design of your circuit into the computer in a way that the circuit board layout program knows about. We're talking about the printed circuit board layout itself, so actually arranging the parts and pieces to be assembled in a and sort of wiring them together, and how you order a board online these days. So let's start by just what is a printed circuit board. It is one or more layers of copper laminated on top of or in between layers of a non-conductive substrate to make a circuit. So rather than showing you that slide example, let me just show you in physical. Oops, full table view there. There we go. So this is an example of a printed circuit board. It's got a non-conductive, in this case, fiberglass core, and we'll talk about cores in a little bit, on top of which, on one side and on the other, are copper that has been selectively etched away to leave little sections that are either that are sort of wiring components together in a permanent fashion on top of this. So the manufacturing process, and we'll have to sort of talk about this as we go through all the different parts of a circuit board, is you put a layer of copper down and then you etch away the places where you don't want copper. You do that on both sides, you connect the two sides together in various ways, and you end up with your printed circuit board. The various parts that make up, well, let's before we dive into like the various bits and pieces, this is why I put this slide in here. Why the heck would you want a printed circuit board? Especially because like the flair of this has been talking about like at a hobbyist level, like making things with Arduinos and things. Why would a hobbyist, especially, why would you want a circuit board? Especially when we spent like a bunch of time in the past 2 weeks talking about perfboard and protoboard and various ways to make things by hand. Well, the biggest advantage of them is that the wiring itself is by definition repeatable, right? If you're building something on a bit of perfboard like we did last week, here's a bit of an example perfboard. Well, this was the example from last week where we sort of abused this piece of perfboard with a bunch of resistors that do nothing. But here's another bit of perfboard from a project in the past that had this 0 insertion force socket on it and some wire. This works for me very well, but if I wanted to build, say, 2 of these and give one to a friend, or if I wanted to build, 5 of them to use for a class, or 25 of them, I would have to basically redo all of this wiring again from scratch, and have to make sure that I get it right every single time. With a circuit board, the wiring is basically baked into the circuit board. It's permanent. And so if you get 5 of these manufactured, they will all work exactly the same way. So you get repeatability in that way. They have consistent electrical properties, so like this goes along with the repeatability. You're not worrying about, okay, did I use a very thin wire for this last time, a very thick wire? Is there some resistance there? If it's a circuit that relies on, is a higher frequency circuit where the lengths of your wires actually matter, those things are all at least going to be consistent from each item of a printed board in a way that a hand-assembled board is not necessarily going to be. Miniaturization and like the ability to even use surface mount parts is a big advantage. So something like, let me pull out, I forget where's our surface mount kit that we can use as an example. Oh yeah, so here, I'll pull out, we'll sort of blend things here. This is one of the little wireless modules that we were in theory gonna be playing with this week. Let me focus there, yeah. So you can see this has some little tiny parts, some little surface mount parts there. And even this chip is, not small, but fairly compact. And that is making it, this would be a hard thing to solder by hand onto a piece of perfboard. I'm just trying to get those connections in the right place. But by making a printed circuit board with connection points in exactly the right places, assembling something small like this becomes a whole heck of a lot easier. So miniaturization and the ability to even use small, especially surface mount parts, is a huge advantage. And then the ability to assemble this by machine. So you can imagine, if you're manufacturing a circuit board to go into 100,000 computers or 100 million iPhones, right? You're not going to have somebody sitting there hand assembling each of those devices. They're going to be assembled by making a printed circuit board and having a machine come and they're called pick and place machines. They pick up a part, they place it on the circuit board in exactly the right place, and they basically go through an oven that melts the solder and flows it onto those parts. So a human doesn't ever have to be involved in the assembly process. Just something that wouldn't be possible with hand assembly. Can be done on the hundreds of millions of iPhone scale. You can now also do it in like the 5 and 10 pieces scale. So if you need, 10 of a thing for your Christmas light installation, or 5 adapters that take, mic level XLR and boost it to a crossover at line level with a bass out and a treble out, and you only need 5 of those, but the circuit layout is a little bit complex. You can actually get those 5 pieces assembled by a low-cost factory now. Of course, like the cost per part is going to be higher than if you were ordering 100,000 of them, but the prices for basic assembly are really not anything huge. So, even in the past few years, this kind of small batch assembly service has become accessible at the 5 and 10 pieces level that it wasn't even just a few years ago, which is really cool for people like us who are just like making a few things. So let's talk a little bit about parts of a oops, sorry, you're seeing behind the scenes there as I refresh my chat, because it's doing some weird size things for me today. We'll go back to the slides there. Let's talk about the parts of a circuit board, like the physical actual parts. And these are some terms that'll, if they don't make sense right now, they'll make more sense when we start to lay out our circuit board. But I want to introduce them just so you have some concept of like what we're talking about this evening. So we'll talk about substrate layers, copper layers, the solder mask, the silk screen, traces, vias, pads. So 8 terms, 7 terms to learn. And again, if they don't track right now, they'll make sense as we start actually using them in practice. So as I sort of referenced earlier, a printed circuit board is made up of layers, like ogres or onions. They have a single, usually, or single or multiple non-conductive layer in the middle called the substrate layer or the dielectric layer, which just means something that does not conduct. And then for a single layer PCB, the cheapest form of PCB refers to having a single layer of copper connections on one side. A double layer PCB has copper on both sides of that, and then they'll be capped by solder mask. So we'll look at all of those things individually. The substrate layer is basically the core material of a PCB. For our hobbyist level things, they're usually rigid, although flexible and semi-flex circuit boards are becoming more accessible at the hobby level. Come on, focus. Focus up there. There we go. So you can sort of see in between the two halves of the circuit board, this sort of like striated pattern in the middle here, that is the substrate layer of this particular circuit board. And this circuit board, it's a fiberglass composite, and most like hobby level purchase circuit boards are going to be this fiberglass material called FR4. It's a fiberglass impregnated with resin. It's fairly rigid. It's fairly indestructible, which is pretty cool. Other materials you might see are FR2, which I'm trying to think. I think this is probably FR2, this like old style, like red-brown circuit board. The color is not necessarily a giveaway. FR2 is a paper laminate, which is impregnated with resin and then pressed. It's a lot cheaper than fiberglass, but it's really brittle. But a lot of really cheap perf board and old style computer boards, like that kind of like flaking apart, disintegrating computer board stuff, is often FR2 made with paper. And then another material you might see sometimes is aluminum in a circuit board. And let me see if I pulled out an aluminum one to demo for you here. I thought I had, but if I haven't, then I don't need to get into tummy cam this early. It's just to show it off. What you often see aluminum circuit boards in is as heat sinks for LED. Oh, here we go. It's buried. There we go. You might have seen these little star mount LED mounts. So that's a high power surface mount LED in the middle there, and this is actually an aluminum printed circuit board because the aluminum is very good at dealing with high heat. It's not necessarily as good at sucking heat away from the actual component as something like copper. Copper's a really good heat conductor, but the aluminum will hold up to heat somewhat better before it becomes soft. So for like heat sinky type PCBs, you often see aluminum as a substrate. Palmer says, aside from sending them out for manufacturing, have you had to etch your own at home? So I have. I have not etched a circuit board in person since Kenneth and I, whom I'm not sure is here tonight. I sort of assume if he was joining us this evening, we would have seen him in the chat by now. But Kenneth and I etched some circuit boards in the garage of his parents' house in high school or early college using muriatic acid and a hot plate, and that was a lot of fun. The gist of the process there's a lot of different ones, but the very common one is using a toner transfer process. You get a printer with toner in it, you print it on a transfer sheet, and then you iron it onto a piece of what's called copper clad, which is just the substrate of the board with solid copper over the top. And then after it's set, what would you call it? The toner acts as a resist. So when you soak that piece of copper clad in acid, wherever there is toner tends not to get etched away, and everything that's exposed gets removed. And so you can sort of remove the parts of the copper layer that you don't want. And then it's up to you whether you want to like actually drill holes in it or not. Palmer says also, are there board colors, are they user preference or is there some meaning to them? They are user preference. So the color of the board is the color of the solder mask on top of the board. And we'll talk about solder mask in just a second here. Green is sort of the default. I don't know why for historical reasons. I think some of the original materials were just green, and now you could have a choice, but most people are still just stocking green. When we look at ordering boards at sort of the very end of the night, you'll see a lot of them are like, the default is green, but now you can also get black or red or blue, but they'll often take a day or two extra and sometimes cost a little bit more. But no, color doesn't mean anything. In fact, if you order from Osh Park, which is the vendor I'm going to recommend that you use if you haven't done this before, all of theirs default to purple. The board house that they work with is like, we just stock a bunch of purple solder mask. There is no meaning to them. I know some people who do more structured prototyping runs will do, you know, initial prototypes in black, or like proof of concepts in black or red. In theory, prototypes are blue and finals are in green or something like that, just so that's like really easy to show at a glance, like, hey, that's a prototype, hey, that's a finished board, or what have you. But no, color is up to choice. Where are we? Oh, one last note on substrates. So thickness of a substrate is something you get to pick at manufacturing time. The sort of default is 1.6 millimeters. That's what I think all of the boards we were looking at tonight are. It's not terribly precise as a measurement in most of the inexpensive board houses, so you can't necessarily count on it being, you know, 1.6 and not 1.4 or 1.2. But when you're asking for a board to get made, just because this is layers of fiberglass that are just layered up to a certain amount, you can order boards that are nominally 1.6 millimeters, 1.2, 0.8, 0.6, down to like 0.4, I think, is the smallest that I've seen. Smaller than that, you get to start to get like into flexible circuit boards or semi-flex, which are made out of a different material. But you wouldn't necessarily make a board out of fiberglass that was that thin, because it would end up flexing anyway, which is probably something you wouldn't want. So looking at substrate thickness is something you can also do. Here's some examples of you know, what the various substrates looks like. FR2 is that paper composite. FR4 is fiberglass, and the FR4, I should say, is what most of the hobbyist level PCBs you'll be ordering are. They're cheap, they're easy, they cut really well at the factory. They're fiberglass composite, and then, like I say, aluminum circuit boards common for like heat sinks and LEDs and things like that. The copper layers. The copper, of course, is forming the electrical connections between different components on your circuit board. For the outer layers, the copper is laminated, it's sort of glued to the substrate. Then a photosensitive mask is applied, basically glued to the top of them. Or I guess a layer of photosensitive glue is applied over the entire layer. Then a laser is shot down in the pattern to set that glue only in the places where you want to keep the copper. Then you basically put the whole thing in a vat of acid, and anything that is not covered by an exposed bit of this photosensitive glue is etched away, leaving only the copper that you have previously covered, and then you use a chemical process to clean the glue off of it, and you're left just with copper in the places that you want it. So when you talk about like etching processes or places that copper has been etched away, that's because they've actually used a vat of acid to remove copper from a solid layer that was once there. We'll see when we get to manufacturing. One of the properties of the copper layers is how thick they are. You can imagine a very, very, very thin layer of copper, and I should say very, very thin, like they are all quite thin. There's not really a dimensionality to them you could see with your naked eye. But the amount of copper can vary, and it's typically measured in ounces or ounces per square foot. You'll sometimes see boards saying this is a 1 ounce copper board. What they mean is 1 ounce of copper per completely filled square foot of copper on the board. 1 ounce is basically the default for most of the hobbyist level board manufacturers, but you'll see lots of them offer, you know, do you want to go to 2 ounce copper as opposed to 1 ounce copper? So you get twice the thickness, twice the height of the copper on that layer, and that just gives you additional current handling capability. That's the main reason you would go to a higher weight of copper. You just get literally thicker copper. It's just like a thicker wire handles current better. So if you're doing like a board that needs to pass 10 amps of switching capability through your power supply or through your FET, one option you have is to make your connections really wide, but you can also make them very thick, very tall. and that gets you extra current carrying. So that's basically the copper layers. Are they able to recover the copper that gets etched away? Yeah, so as far as I know, and I will say I put a link in the description to a video by Strange Parts with Scotty Allen, who does factory tours of various places. He did a tour of the JLC PCB factory a while back. Does a nice job of walking through all the various steps in PCB manufacturing, which is really cool. And I believe they are able to basically take the hydrochloric acid becomes hydrochloric acid and cupric sulfide. I might be making that up. But they are able to basically reverse that process and recover the copper from it. It doesn't go back into their like copper manufacturing. It goes to a copper recycler, I think. But it's not just wasted copper on the board there. Good question. So the copper layer is the layer of connections on your board. Because it is basically glued to your substrate, you can cause that copper layer to what's called delaminate from your boards. Basically, that copper can peel away from the underlying substrate. If you apply too much heat, or really I see if you heat the same spot over and over again, and each time it's exposed to a little bit of stress as it's heating and warping, and finally that copper in a little localized area just falls off your board. You see like an individual pad where something is connected will just come right off. So something to be aware of. Your copper layer will also, as the layer that's doing the wiring more or less, there will be restrictions from your board manufacturer onto the minimum feature sizes you can use. So how close things can be together, how without them being able to guarantee like, hey, if these things are closer than a certain small amount, we can't guarantee that the acid is really going to get down into that feature and cause separation. There might be a short in there, and that's true of adjacent lines or holes or various things. Will be various specs, and we'll look at them a little bit as we go along. But just know that like all those limitations are basically based on the copper layer and how finally they are able to protect and selectively etch away bits of copper on your board. One thing that goes on top of the copper layer, and Palmer, this is the thing you hit on earlier that causes the color of the board, is the solder mask, which is just a layer of a lacquer-like material. So it starts as a liquid and then they bake it to solid that solder does not adhere to. So all of the green on this circuit board, say, is solder mask. You can tell the only things that are not green are either these white lines, these labels of the silkscreen that we'll talk about in a second, or these silvery areas here where we actually want to solder components. And this helps a great deal when we're soldering things to a circuit board. It means if we accidentally, slip and say, if we're soldering these three connections right here, solder's not going to want to stick to the physical circuit board in between those three connections. And that's going to help us not to make a solder bridge there, unless we really try or really slip. Or, if we bodge a bunch of solder on there and get them to stick together, we certainly can. But having the solder mask in between each of those connections is going to help us not make boo-boos. And it does the same for machine assembled parts where, where a machine is placing a component down onto some paste-like solder and then just feeding a thing through an oven. That helps the solder not to flow where it's not wanted and stay on the individual pads, the points of connection where the solder is supposed to be. In the same way that there are clearance rules for copper features, there are clearance rules for solder mask. You can see, like, in this example picture, which is just something I stole off the internet, some places between these very small connection points had the solder mask, which I'm sure you would want, and some are just too narrow for that solder mask to have gone through. So again, you want to respect the rules that your board house has put out if you want solder mask in between each of those pins. And we'll look at what those specs are, how you find them, and so on as we go on. You can also, the solder mask is typically semi-transparent, and also you can tell so for example, let's see if we can get this to focus here. So this is a trace on this particular circuit board here. Let's look at this trace going off this way. So there's solder mask over the entire area. There's no bump there, but because it's semi-transparent, we can tell that there's a copper trace, a copper wire essentially going this way, and then two little gaps on either side. So just because there's this solder mask over the top doesn't mean that we can't see what's going on with the traces underneath. We're looking at a translucent solder layer over the copper layers. I should say, just to skip back a little bit, we're going to be working primarily with 2-layer boards tonight. Let's come back over here. We'll be working only with 2-layer boards tonight. There are multi-layer boards, and for a professional design, you would often go to a 4 or 6 or 8-layer board. And when we talk about a multi-layer board, what we're really talking about is the number of copper layers that are in that circuit board. So here's a cutaway that I think I stole from Wikipedia. You can see this board has a top layer of copper where the traces are on the surface. Then it has this white layer of substrate. Underneath that substrate is another layer of copper traces that I'm doing, could be the same or different connections under here. Then we have a layer of what's called of a core layer, right? That is basically a glue between adjacent layers. Another layer of copper, another layer of copper. You can build them up all the way down. Most of the free programs for laying out circuit boards only let you do 2-layer boards. You have to pay for the versions that make you do 4 or 6 or 8-layer boards. But the reasons you would use a multi-layer board are if you had a part with lots and lots of pins that you physically couldn't figure out how to make all the connections on just a 2-layer board. Going to a multi-layer board literally gives you more physical planes to route those connections through. It's very common to see a 4-layer board, which would be typically or commonly would be a 4-layer board. Like one layer would be entirely ground connections, one layer would be entirely power connections, and that leaves you 2 layers to route your signals along. When we're doing our 2-layer boards, like we're working with tonight, we have to route power and ground and signals all in those 2 layers, and that can make things a little bit tricky. But also at the scales we're working, we're not talking about routing the connections for say a computer CPU that might have 1,000 connections. We're probably working with a chip that has, at most 30 points of connection. Working with that on a 2-layer board is a much more feasible thing. Palmer asked, does multi-layer boards get etched as 2-layer and then glued together? Essentially, yes. They would get, so you end up with a what's called a pre-preg layer, which is a layer of fiberglass with resin in it that gets its copper layers basically built on it, etched, and then that gets glued to another pair of copper layers and another pair of copper layers until you've built up the whole thing. You should check out the Strange Parts video that I linked. It does a nice version of building that up. The way that they do the top layer and the bottom layer is slightly different to how they do the inner layers, but essentially, they're basically gluing the layers on top of each other one layer at a time, and then they use a big heated press to basically compress and activate all those resin glues and seal it into a solid board. Let's see, we talked about solder mask. Silkscreen. So silkscreen is the labeling on the circuit board. That's the little white lines that you see everywhere. Silkscreen is almost always white, although there are some people who've been experimenting with RGB processes. Depending on who your manufacturer is, these may be actual silk screens, like the same way you would screen print a t-shirt. You'd have a big screen of silk that you'd blop some pigment onto. You'd lay a mask underneath that you've printed out on a laser etcher, basically, and then a big robotic squeegee comes across and presses that paint through the layer of silk only into the places on your circuit board where you want those labels. There are a couple other processes called LPI and DPI, which are basically inkjet printing onto a circuit board, which is really cool. They're more expensive because the machines are newer and more expensive, but they give you a lot higher resolution. One of the limitations on silk screening is minimum resolution size, because the ink actually has to pass through holes in a physical screen of silk. So when you look at limitations from your board house, you'll see hey, the smallest line we can guarantee on a silk screen, is such and such dimension wide, and the closest, the smallest that fonts can be and text can be is a certain size. Otherwise, they'll be unintelligible. So, and that's something we'll look at in a little bit too. The silk screen is basically ink or lacquer printed on top of either the front or the back or both of your circuit boards. You can do double-sided silk screens, for example. A few more things to talk about before we dive into the development process, which if I feel like I'm jamming ahead a little bit here, this is all super important stuff, but I'm excited to start laying out circuit boards with y'all this evening. I think that'll be a jolly good time. So 3 more terms we need to learn. Trace is one that I think I've tossed out a little bit already tonight. Trace is just the term for basically a copper wire on a circuit board, a piece of copper connection that sits on top of your substrate layer here and carries, or inside in the case of a multi-layer board, and carries your power, your ground, your signal connections, what have you. So rather than saying like wire, which implies a free-floating thing, we use the word trace to refer to an individual bit of copper connection. Widths in circuit boards, much like we were talking about last week with circuit mount components, are typically measured, well, if you're working in imperial units, are measured in mil, which is thousandths of an inch. So you see that, the width of this trace is 8 mil or 12 mil or 20 mil, 8 thousandths of an inch or 20 thousandths of an inch or what have you. When we're talking about sizes, you can also work in millimeters, and ultimately, since the process of etching away at this at the copper is a more or less analog process, you can specify whatever widths you want. There's not sort of a standard size of trace, although there are some reasons to pick larger or smaller sizes, as we'll see in a little bit. But typically, if you're working in imperial inches, and I will be tonight, mil is the width that you're working in. Chris points out there may be font restrictions on your board house. Yeah, so we'll be. I have definitely screwed this up before. It had my labels come out all strange because the way that font labels are stored in the kind of files that you send to your board house is really not great. The newest version of formatting allows you, like the newest version of like Altium or Eagle software will let you sort of pick a system font and will translate that basically into artwork for you so that it comes out as like a raster image that you can send to them. But for a long time, you really only had like 2 fonts that you could use. Chris has also messed up fonts. Yeah, it sucks. And things just never don't come out looking right if they don't agree. 2 more terms. Via is something we should know. So a via is 2 pads on different copper layers that are connected by a conductive hole or column through your PCB. So if we look at this cross section here, we'll see we have a trace on this top layer. We have a trace presumably down on this bottom layer here that we can't see. And we have this via of copper that's punched all the way through the board that connects this top layer to the bottom layer. We can see in a multi-layer board, it connects to any of the middle copper layers too. And we won't be going into this tonight, but just so you know the terms, if you have a multi-layer copper board, you sometimes, depending on your manufacturer, have the choice of a via that doesn't go through all the layers, that might only go through, say, a top couple here, or a via that only goes through a couple of the internal layers. Or, when I say a couple, it could be 2 layers, it could be 4 layers, but just doesn't go through all of them. This style here, where it starts on the outside and goes in but doesn't pass all the way through, is called a blind via, and these internal ones are called buried vias. Not all manufacturing processes allow these. Some do, some don't, and they usually they may have different specifications than a via that goes all the way through. A via is basically how you get a signal or power from one copper layer to another. There are multiple styles, whether this core is hollow or filled in, but essentially their purpose is to get current from one copper layer to another. And then the last term I want to touch on before we jump into actually laying out our circuit board is a pad. Pad is just, I know I have used this term before and not really explained it. A pad is an exposed area of copper for a component to be soldered onto. So whether we're talking about a surface mount part, where there's just going to be some exposed copper, or we're going to be talking about a through hole pad that has some copper exposed and then a hole down the middle for the lead of the component to stick through. Either way, we're talking about either an SMD, a surface mount pad, or a THT, a through hole pad, is the point where components actually attach to. Brief side note, so I keep saying these are exposed copper for components to be attached to, but you'll notice both on the pictures there and on these physical circuit boards that often the pads are silver, although not always, right? So here's a board where the pads are sort of that nice yellow coppery color that we know, and here's a board where they are silver. What's the deal with silver? Is it an aluminum layer? What's going on there? So that silvery surface is actually a very thin layer of solder that the factory factory applies as part of their manufacturing process. This is what's called a hassle coating, H-A-S-L. I don't know that anyone actually says hassle except me, H-A-S-L. H-A-S-L is hot air solder leveling. And what happens is after the board is fabricated and it has a solder mask on it, so the solder's not going to stick where we don't want it, it gets a treatment in flux and then dipped into a vat of liquid solder that sticks just to those pads, and then a machine comes and blows a jet of hot air across the top of your board, so you're left with this very, very thin layer of solder pre-applied to your board, and that's to make soldering, either by hand or by machine, easier. So you have this very, very small bit of solder that's already done the work of sticking to the copper layer, and now we're basically soldering directly to that. It's not enough solder that you ever actually really notice it if you're hand soldering. Like, the amount that you're applying with your soldering iron is so much more than is on the board. But that's just a nice feature of circuit board manufacturing. There are many kinds of surface finishes that you may see. Hassle is kind of the default, the cheapest. It's a lead-based process typically, so if you're trying to be lead-free, you might go with either a lead-free HASL process, which is the same thing but with lead-free solder. There's also something called ENIG, E-N-I-G, that you might see. Oh, hey, Chris, you're asking about ENIG now. Yes, we're so in sync tonight, yes. ENIG is a reference to, so ENIG stands for electroless nickel, something gold. I forget what the I is. Electroless nickel impregnated gold? That's not right. But what that is a process by which, so same step in the manufacturing process, there's exposed copper pads. They treat them with a very fine layer of nickel, which acts as an electrode. Nickel immersion gold, yes. So, so they coat it in a very thin layer of nickel. Then they dip that nickel into a vat of a molten gold solution, and that solution causes a chemical reaction to happen with the nickel on the surface of the pads, and that causes a very thin layer of gold to stick to your copper layer of your pads. Gold is a really good electrical conductor. It's also very expensive. But in the amounts we're talking about, right, we're not talking about a lot of gold, but if you have a connection that absolutely needs to be low conductivity, like the connectors in a computer CPU, or a very high powers like edge connector that like we're going to shove into the edge of a card and we're not sure where exactly it's going to line up, but it better be a good electrical connection, you might go with an ENIG process to get that layer of gold on there. Electroless refers to the fact that you don't have to use the nickel as an electrode to attract the gold to it. There's actually a chemical process that binds the gold to the board. Hey Travis, how are you doing? How are things tonight? Is there a limit to the amount of layers a board can have? In theory, no. Practically, yes. As Chris says, it depends how much you want to spend. You can buy at a hobbyist level anything up to like an 8 or 10 layer board. There's no reason that a contract manufacturer couldn't make you a 10 or a 12 or a 16 layer board. But those would be pretty specialized use cases. Something like a computer motherboard, maybe. And I keep coming back to this like computer CPU because that's the kind of part that has thousands of points of connection in an area that's maybe a 1.5 inch square. So having those extra layers to be able to do what's called the fan out, where you take all those points of connection that are very close and get them out to where they're useful, having multiple layers is really useful for something like that. I have only ever, I'll be honest, ordered 2-layer boards just as like a hobbyist. I've worked with 4-layer boards. The nice thing about 2-layer boards, especially if you're doing prototyping, is that of course there's a copper layer on one side and a copper layer on the other side, so everything's exposed. So if you've messed something up, which that would never happen, you can not only can you see it on the surface of your board, but sometimes you can fix it, say by scraping away a little bit of the copper layer, and now you've broken a connection in addition to being able to add connections between points. If you have interior layers, and like I say, that can make your life better in terms of just the ability to route more things, you also can't access all of those connections. So your options at that point may be limited to spinning a new board. Palmer says, did I design this PCB I'm showing? Yeah, actually, I just grabbed the one that was on. I have such a pile of PCBs surrounding the table here, so I'm staying very zoomed in because the board is a mess. But yes, this is a PCB I designed. This is a circuit board that is a radio frequency amplifier. I may have mentioned I'm a ham radio nerd. This board is a 50-watt amplifier for up to for a specific ham radio band, just to be determined by this low pass filter here. So it would take in fact, if you don't mind a little tummy cam here, we'll just come to just the table. You can stare at that. I think I might have an assembled version of this board I can show off. And then we should get to actually laying out our circuit and designing our circuit board. One of the perks of this new microphone setup, although you can't see it here, is that it's wireless. So I can I can step away and I still have connectivity to the computer, which is kind of nice. So this, although it's in a 3D printed case now, this is the assembled version of that same circuit board. So you can see this is where, over on this side, I've got a couple of, I've removed the connectors for some experiments. RF energy comes in here, goes through this relay. If the system is not energized, these relays basically pass the input signal directly through the normally closed contacts on this relay, through this relay and out, so things aren't amplified. If the system is on, if it's getting power, say in through one of these Anderson power pole jacks here, these two FETs act as a push-pull amplifier to amplify it, and then this transformer and the low-pass filter, which would go here, take that power output up to something like between 30 and 50 watts. As Travis points out, it's not a perfect design. There is a bodge wire there. So part of the feature of this amplifier was it has an RF sensing circuit, so that when it senses RF energy coming in on the input side, it automatically, senses that using this circuitry here, switches the relays on, and causes it to pass through the rest of this circuitry. I made a boo-boo in how I wired it in, so I did a little bodge wiring there to take the signal from where the input was and get it to where it needed to go in the circuit. Looks like some post-arrival work with a solar center. Oh yeah, so this dates back to, this is a project from a couple years ago, before I understood how to do board outlines in EagleWell. So I meant for this entire area in the middle to be nice and cut out by the factory, although it would have still been a little bit small, and it showed up instead with these two little holes. So with a nibbler and some filing, I've ended up with the holes that I needed. But yes, this will be another like do as I say, not as I do, and we'll look at how to do board outlines in Eagle, so that the factory will cut those holes for you, instead of having to chip them away by hand. So learn from my mistakes. I certainly have. By the time it came to do this project, I had learned how to do, have the factory do this nice, crisp, clean routing, which is lovely. So that's always an option. Chris says, I bet you're going to cover it, but yay or nay putting components on both sides of a board? What a good question. So matter of opinion a little bit. It depends what you're going to use it for and what your ultimate goal is. So to take some specific examples, this board I knew I was going to mount in a box like this, and it was going to be experimental, and I want to get at all the components. So doing all the components on a single side was really helpful. For most hobbyist level boards, if size is not a specific constraint, I recommend, if you can, keeping all of your components to a single side. That said, as we looked at last week, there's nothing wrong with putting components on multiple sides of a board, especially if you're really trying to keep things small. Just looking to see if I have that little, oh yeah, here's the little dip switch board we were working on. Yank that off of here. So this is a little board that I've been working with recently that is a little dip switch on one side and the ICs on the other, and I really, really wanted this to be small. For hand manufacturing, this of course doesn't really add any complications. For machine manufacturing, if your goal is to ultimately make a thing that a factory is going to make for you, and by a factory, that could mean I want to sell this as a product for 100,000 units, which I have never done, but could also mean hey, I might want to have 25 or 100 of these made for a project. Having components on both sides make the manufacturing process significantly harder. So worth staying single-sided for cost's sake if you're looking at pick and place machine assembly. For a hobbyist level board, if you have space constraints, there really is not a disadvantage to doing a two-sided board. So that's my 2 cents on single versus double. I think we've covered all of our components here. So let's cover briefly. We're here? Yeah. I'll cover briefly the design process that we'll be going through this evening. of getting an idea, turn ourselves from an idea into a circuit board. So first we'll need to do some schematic capture, which is getting the design laid out in the computer program itself. I should say in this case we're going to be using Autodesk Eagle, which is Autodesk's free for hobbyists PCB design program. It's very full-featured. The only things, as I say, that the free version doesn't do is multi-layer boards, and you're limited to a certain size. I want to say it's like 4 inches by 4 inches in the free version. But that's a great place to start, and honestly, like that's a very reasonable size to make most hobbyist circuits with. So we'll capture our schematic, then we're going to, we're going to lay out the components on our circuit board. We'll do our PCB layout, then we'll route the board, which is to actually place the traces onto that board to connect the various components in the way that they are in our schematic. We'll have some tidying up to do, and then we'll look at how you take those files and send them to a manufacturer online to get the thing actually made and shipped to you. It's a pretty straightforward process. So I think that's it. So today's circuit, like I say, one of the things that I wanted to do was pick a circuit that I had made in the past that I already basically had the circuit board here for. So as we're making the board and looking at like, oh, so when you do this, it creates a via. When you do this, it creates a pad. We'll be able to say, and that will look like, and we'll be able to look at the physical circuit board on the table, rather than like designing a circuit board and then in 2 weeks' time when it was here, we could look at it all together. So I think that'll be useful. So we're going to use a circuit that I have actually made a circuit board for, which is a DMX sender or receiver board for an Arduino Pro Mini. Just by the faces, the names in the chat tonight, I know there are some DMX nerds out there already tonight and some theater people. If DMX is not something you've ever heard of before, this is really all we'll need to know about it. It is a balanced transmission protocol used a lot in stage lighting. It's based on a physical layer called RS-485. It basically has two signal lines, one of which will be high when the other is low, and one which will be low when the one is high. And we basically need an extra bit of circuitry to take those alternating high and low signals and turn them into a single line signal that the Arduino can interpret as data, or vice versa, that the Arduino can use a single digital data line pulsing high and low to create that alternating balanced signal in the output lines. Tonight is about the process of laying out a circuit board, not so much about the physical properties of the circuit itself. We should talk some other time about like circuit design, I guess, like how you actually think about stringing together the components to make a circuit. Tonight's more about like taking that circuit and turning it into a circuit board, if that makes sense. So like I said, if you've never heard of DMX before, don't worry about it. You really won't need to know that much about it. In fact, the circuit that we're working with is this Jeff Glasscad style of things, right? Where things are drawn in Google Slides. This is the whole of the Google Slides version of the schematic we'll be working with tonight. We'll be making it for the Arduino Pro Mini, which we've looked at here before. It's exactly the same connections as the Arduino Uno that we know and love, just in a tinier little form factor. Same chip driving all the things, get a reset button there. There's an LED on there that's built in. But instead of having these, just spilled a little beer. No problem. You can't see it, so it's fine. Didn't spill on anything electronic. There's nothing electronic on the workbench. It's fine. Oops. So the main difference is instead of having these big female headers here, we have these male pins that we can plug into a prototype board. So I like making things for this little tiny form factor if I'm trying to keep them compact. Just makes life a little bit easier, keeps things a little smaller. Well, I'm just gonna take a second and mop up some of this beer spill that I've had. I've had that much of beer tonight. I haven't dipped into this crowler hardly at all, and we're already getting sloppy. So maybe it's a good thing that I'm splitting this with the wife. I think that seems like a good thing. But the beer, Travis, is I think I had to show it on this camera before. Is Snick 3 from Beguile Brewing Co. in a crowler size. It's all good, Travis. Like I say, like some people are out there like probably on their laptops following along. Some people, I would bet money, are not wearing pants and they're like showing up whenever, and that's totally cool. Like I say, I'm not drinking the whole crowler tonight. It's split in half, and I drank maybe 2 ounces, but clearly wasted already. Speaking of wasted, I have no segue. This is the schematic that we're going to be playing with tonight. So we're going to use this chip, this Max 485 chip. That's one of many options for chips that turn this DMX protocol, which comes in on a couple of wires, we'll call A and B, comes into the A and B inputs. We have a single data line that goes from this R0, this receive output, to a pin on the Arduino. We can use the TX pin on the Arduino to go into a data input chip to send data out. We need one control pin to tell the chip whether it's supposed to be a receiver or a transmitter. And then both the Arduino and the Max 485 will need a 5-volt line for some power and a ground line. And then we'll need some way to connect this thing to the outside world. So we'll stick a little connection point on it for our A signal line, our B signal line, and ground. And like I say, that's the schematic we're going to be working with tonight. If all of this has been Greek because DMX is new, just know that we have to take a couple of signal lines that will always be opposite each other, and we have this chip that turns it into either a single data line to receive it, or takes in a single data line and generates that signal for us, and then we use a control pin to determine which of those two functions we're using. Here's a little value from the data sheet. Oh, hey, Nate. Nate was about 10 minutes late, but is wearing clothes. So a little column A, a little column B there tonight. Totally good. Since I was good I avoided tummy cam tonight, you'll never know whether I'm wearing pants or not. I am, but you would never know. Palmer, I want to come back to your question in just a second here. Just to give you a little glimpse at this Max 485 circuit here, just to make sure we're sort of on the same page about what it's doing. It has basically 8 points of connection here. It takes in this balanced signal on a couple of points coming on a couple of the pins, VCC and ground, so it's got a power and a ground. It's got a data out, it's got a data in, and then it's got a couple of control lines in the middle here to determine whether it's supposed to be sending or receiving. That's all the chip is doing. So when we'll need to route those connections into RIC. That next slide is a cheat slide for me later to refer to, which means that we are ready to dive into our schematic layout process. Palmer's question was, what kind of voltage difference on a board would we think about separation of traces? So it actually depends whether you're talking about traces on the same layer or traces on different layers. Because the substrate layer is a dielectric, so it doesn't want to conduct electricity, you can put... I would, for safety reasons, anything above, 24 volts, you should be doing the actual research and not trusting a guy on YouTube to look at. But you would be fine, you can put up to maybe 1,000 volts between traces that are 1.6 millimeters apart on standard FR4 material, because, of course, the material that your substrate layer is made of is going to affect whether it's going to break down and conduct or not. Adjacent traces on a single layer you'd want to be more careful about. For anything above 24 volts DC, I would go and look it up in a calculator. You really don't need much air spacing to prevent shorting across things. Yeah, anything above low voltage DC, I would just double check on an online calculator. You could probably keep, if you think about an iPhone charger, for example, that has 120 volts AC in one place on the charger and 5 volts DC in another, and the separation gaps on those are 200 mil, 0.2 inches or so. So you don't need a ton of separation, but really anywhere where the voltage is high enough for you to consider it a safety hazard if you were going to grab it, I would check it out and do the research. If that makes any sense. A little bit of a cop-out answer, but I'd rather you look it up and be safe than trust me, if that makes sense. Yeah, good question, though. Thinking about limitations on circuit boards. Why don't we get into some circuit layout? So I'm going to be using, get out of there, Eagle PCB design software. I should say, so I reconfigured my displays a little bit for this evening, just to try and make this interface sort of as visible on stream as possible. It's kind of blowing everything up for me here. So your interface may look a little bit more, the aspect ratios are probably a little bit more sensible. I mostly wanted to make sure that we could potentially read the text and menus and things. And especially when we get into the layout program, all the tools are going to stack up next to each other. If yours looks much more like a single line of small tools than a big bucket of large tools, that's just an artifact of how zoomed in we are tonight. So this is Eagle, I think version 9.6.2, which is the most recent one. This is the free version. It's free to download online. I think I put a link in the description. If not, you can Google Autodesk Eagle PCB, and it will pop you up with the free version. You have to make an Autodesk account, but they really just want to send you promotional emails. I've had an account for 10 years and never bought anything from them, and we're doing just fine. The only limitations, like I say, on the free version are total board size, and you can only do 2 copper layers, which for our purposes will be fine. So when you first open up the program, this is the interface that you get. And just to point out some of the buckets on the left-hand side here that are useful to us, we have this projects bucket, which contains some examples that you're welcome to pour through, and then any of the projects that sort of hold a number of related schematics or boards together, any project that you're working on, and we'll be making one of those in a sec. Spice models relates to electrical simulation, which I have not played with in Eagle. I have other Spice tools that I use. Cam job scripts, ULPs are not, don't worry about too much. Design rules are where you can store. Many manufacturers will either publish or either like a written version of like what all the limitations as far as how close copper can be to copper, how small your silkscreen details can be, and so on. Sometimes you can just download a file that has all those things in it, or you can put them into Eagle by hand. And so you can store various sets of files that say, all right, if I'm getting manufactured by, say, you know, JLC PCB's cheapest service, the rules are this. If I'm going through PCBWay and I'm paying quite a bit more, the rules are this. And you can sort of store those separately. And we'll look at how you basically automatically check those rules on your circuit board a little bit later tonight. Design blocks are a way of storing a group of components that often act together as sort of a single drag and drop thing. So let's say, for example, like this DMX block that we're going to do tonight, you know, I always know is going to need like these 5 components, and here's a useful layout for them. And I don't want to redo that layout for everything that I build that uses this DMX protocol. I could create a design block that is that those components sort of defined in that arrangement, and sort of drag and drop that into future designs, which is kind of a useful thing. And then libraries are the collections of parts, either ones that you've made or ones you've downloaded from the internet or ones that come with Eagle, that you can use to build up your circuit. So libraries hold the parts that we're going to use. Cool. So we will start by coming up to the File menu, going to New, and we'll make a new project. We will call this, I'm going to call mine Stream 614, but you can call yours whatever you want. You'll see it's added this green dot next to it here. Oops, green dot. Yeah, so which will tell me that it's a, that is my active project at the moment. Now, once I've got that project activated, as I toggle this arrow on and off, there's nothing in my project yet. So let's start by creating a new schematic, which will hold the circuit design of our project. So I'll come up to New, and I'll select Schematic from my File menu here. Chris says, from what I can tell, Fusion 360 doesn't have board limits. Ooh, sorry. That's going to be really obnoxious as I reset that mic. There we go. Yeah, that's worth pointing out. So Eagle and Fusion 360 are both made by Autodesk software. And in the most recent version of Fusion, you can actually design circuit boards directly in Fusion 360. I've played with it some. I think the interface is a lot less intuitive, but that might be because I've been working with Eagle for 10 years. So this might just be old fuddy-duddy syndrome. One of the cool things about that is, you know, while you can design a circuit board in Eagle, import it into Fusion, use that to do your physical design around your circuit board, the idea of doing both of those things in the same tool is a really cool idea. I just think the interface is a little bit confusing. So I'm working in the original Eagle tonight, but if you're interested, certainly play around with this. Everything that's possible in this software is in theory possible in Fusion 360, which is a 3D design program natively. So worth playing around with. I'm going to show you how to do it in this version of Eagle. But Chris points out that maybe Fusion 360's version doesn't have limits on board size, which would be a pretty cool plus to the free version of this program. So here we've got a blank schematic for us to start building our circuit in. Now, the first time you open up the schematic editor, if you're new to Eagle, it may look something more like this, where you have a bunch of ancillary windows and menus popped up here. I'm going to encourage you to go ahead and close all of those windows and just leave yourself with the empty schematic. You can always turn them back on from the View menu here. There are things that are like the selection filter menu that says I want to only be able to select certain types of things, or the inspector to tell you the properties of something you click on. They're all very useful, but for cleanliness, I say start by turning them off and leaving yourself with a a blank screen to work with. So this is the interface of the schematic editor of Fusion 360 of Eagle PCB layout software. There's some sort of familiar icons up at the top: open, save, print. We've got some zoom commands up at the top here. We've got some design link commands, which you can't see, but at the top, design link, that's for linking your design to Fusion 360 and others. We have a layer menu, so when we add something, it's going to be on a specific layer. Often this will be taken care of automatically for you, but if you wanted to set it manually, you can. And then there's some testing tools here if you're doing circuit simulation, which we won't get into today, because honestly, I'm not that familiar with the tools that are in Eagle, but they're there if you wanted to play around with them. Down on the left side here, this is all of the, let me make sure I maximized correctly. This is all of the tools that we have available to ourselves, and we'll sort of introduce them as we need them tonight. Yours probably looks like a long single line of tools. Mine is sort of stacked up like this again because I'm zoomed way in so we can sort of see things a little bit better. But as you mouse over them, they will tell you what they are, and I guess I will introduce them as we need them. The other thing I will point out is up at the top of the screen here is your command line. So in the theme of Autodesk products, like AutoCAD, most of them are programmable either through a graphical user interface like this or through actually typing commands on the command line. So for example, if I wanted to use a command like the move command, which we'll see in a little bit, but you can imagine it moves stuff around the screen. I can either click on the move command here, and we'll see it's given me some controls up at the top, and I could move something here. Or I could type move into the command line, and it would do the same exact thing. You can also use that to add various parameters to your commands. You can also use that as basically as a scripting language. And again, we're not going to get super deep into this tonight, but if you wanted to have a script that automatically, moved something 200 mil this way, rotated it 90 degrees, and removed all its connections, you could write a little script and then execute it on parts. That's beyond the scope of this evening, but just a cool feature if you wanted to go and play with it. And I should say, there's going to be like a fair amount of this evening that's like, here's the basics of laying out a circuit board, and here's a little apple you could go pick up and take a bite of and investigate more of if you wanted to. But for the sake of keeping things streamlined, I'm just going to throw out little nuggets at you, and you can dip them in the barbecue sauce if you choose to. So let's start laying out our circuit. Remember, our circuit that we're going to lay out is this guy. So it's going to need a place to plug in an Arduino Pro Mini. We're going to need this Max 485 chip on the board. We're going to need a header connector, someplace to attach our DMX signals. And we're going to need a couple of resistors for a reason that I'll talk about in a little bit related to how this signal protocol works. So let's start getting some components into our schematic. The command for getting a component into your schematic is the add command, which you can either do, it's the little command that looks like a little OR gate with a plus symbol on it down here, or you can type add into the command line, and it will bring up that got huge. The zoomed inness here is doing weird things to how it thinks maximized Windows work in Windows because Windows. But when you add something, it brings up basically a list of all of your libraries, all of your collections of parts that you could possibly drop into your program. There's all kinds of stuff in here. And as you open up a library here and click through the various subcategories, here's a Euro card with VG64AC connector on it. Here's some chips from Allegro software and all kinds of things. So to be perfectly honest, it's not always obvious where a specific part would hide in these libraries. Often you end up just being like, hey, Googling where do such and such parts live in Eagle? And it'll be like, oh, those are in a library called lists. And we'll see a couple of those later today. In theory, they're all laid out kind of by manufacturer. But then generics are arranged either by like here's generic fuses, but are they really generic? So the part labeling scheme is not great in the libraries, I will say. Thankfully, Maxim, who makes the chip, the Max 485 that we're using tonight, is in their known proper library, the Maxim library. And if we toggle that open, we see a list of all the parts that Maxim has in their library here. We will get to building your own parts in an Eagle library later tonight, because that actually is a fairly large part of building your own PCB. Even with a couple thousand components and libraries here, you're always going to be picking 1 or 2 or 10 that don't exist in these, and you'll be making your own parts, your own library of parts to add to your circuit boards. It's really straightforward, and we'll do it for a switch later this evening. So what I'm going to do first, I'm going to get my Max 485 part onto my circuit board here. And I'm going to scroll down until I see, so the Max 485 is actually the same chip as the Max 481. If we look at the data sheet here, we'll see the Max 481, 483, 485, 487 are all basically variants of the same thing. So in my Max library here, I actually have 3 listings for Max 481. And if I look up here, I can see this one is a through-hole part. I know because it has these green pads, which I know are going to be through-hole pads. I've also got this in an SO08 footprint here, and this little tiny one in a UMax 8 footprint. Circuit footprints are more or less standardized. A dual inline chip is going to be a dual inline, the same dimensions from between manufacturers. An SO8 chip is going to be the same, and so on. And I know that the chips that I have bought for this project are in the SO8 surface mount form factor. So I'm going to go ahead and add that to my circuit. What does Chris say? That one symbol looks like a plug on a cord. The symbol looks like an OR gate. Yeah, sure. The add icon, it looks like whatever it looks like to you, let's say. So once I've selected my part in here and I've checked that it's the right footprint, the right manufacturer, I can hit OK, and it attaches to my mouse here, and I can click to place it somewhere on my circuit board. Or on my schematic layout here. So let's place it just there, and we'll see that it has dropped itself onto my circuit diagram here, and it looks a lot like the drawing from the slides that we saw earlier, and that's not an accident because I stole them both from the same place. We can see we have our connections, our data in, our data out, our control line, our power, our signal lines. Although we don't have our power and ground connections, you'll notice here, and we'll get to that in just a moment here. But basically, this is the symbol in your schematic that represents that part. Now, this one, because it's a relatively small part, the layout of the connections kind of mirrors the layout on the physical pins. If we go back to our drawing of those physical pins here, we can see like data out, control, data in, control kind of mirrors the connections in the schematic. There's no reason it has to be that way, and in fact, for larger parts, it usually is more convenient to lay out the pins in a different logical order. This is just a simple small part, and so they've done us things are laid out basically the same as they are in the chip, and that makes it a little easier for us to grok what's going on. Palmer says, have you designed the size of your circuit board yet, or do you do that once your circuit is designed? Good question. So right now, Palmer, as Chris points out, we're just capturing that schematic into the software, and then we'll get to laying out the board as the second step. And actually, we'll do a little bit of going back and forth so you can see how that interplay works. Real quick, I want to show you, so this is pretty common if you're working with integrated circuits. You'll notice that this part has our data connections here, but doesn't have our power pins. And that's simply because often, if you're working on a board that has 5 or 8 or 10 of these chips, the power connects to a power rail, ground connects to ground, and they don't really have anything to do with like where this chip exists in the circuit. So often, the symbol designer, the part designer who's working with the Eagle library, has sort of hidden those in a different place so you can separate them from your pins. So here, let me show you what I mean. We're going to use the invoke command, which looks like, I guess, 2 little electrical plugs if you're in Palmer, or 2 little OR gates over here. You can also type invoke into the command line. That's going to give you the invoke command, and when you click on a part, it's going to tell you the various components of that symbol. In this case, it says, I've given you this one already. There's 1 of this chip already in the sheet. There are 0 of this VCC and ground pin. So if I hit invoke and click OK on that, it gives me 2 other pins to drop into our circuit diagram, which are VCC and ground. So these are the power and ground connections for this chip here. And you'll see this is IC1, integrated circuit 1. It's sort of done some automatic labeling for me. And these are IC1P. These are the power pins for IC1. This would be really useful for, let's say we had 10 of these chips on a board. We could wire them all together in all of this space in a way that made sense to us, and then just basically connect all of the little power and ground pins, just put them all next to each other, hook them up to power and ground on our schematic editor, and we're sort of done. They're sort of thinking about them as separate from the logic of our circuit here. But if you're wondering where your power and ground pins are for your chip, use the invoke command to get them to show up. Cool? So now that chip is on our board, let's give ourselves something to connect it to. Let's put in this header connection here where we're ultimately going to connect our chip, connect our signal lines to. And I guess just to show you on the physical circuit board, because that was sort of the point of doing this. So this is the circuit board that we are ultimately going to be building today. Isn't it adorable? It's so cute. So what we just placed was the component for our little Max 485 chip here. Let's give ourselves these little through-hole header connections here where we might ultimately solder some wires to connect this to our system. I also have here, it's not exactly the same version, it's a very similar, an assembled version of the circuit that we're building today. And you can see those little header connections, much like the little places, the little pads on a piece of perfboard that are meant for, you know, a wire or a header to be soldered into. Let's give ourselves some little holes, some generic holes to solder some wire into. So those kind of connections in the Eagle library, and this is one of those places where it's just like, where does that part live? What do you call that? A thing I Googled once and now know, and now I'll share with you. Let's add another part. I'll type add into the command line. I'm going to close my Maxim library so it's not taking up all this space. Get out of here, Maxim library. Header connections, those sort of hole connections that we might attach things to, live in the pinhead library. No, I'm not joking. Pinhead, like pin header, like a header connection that you might attach a header pin to, which is the term for these little metallic prongs that we plug into breadboards and things, are pin headers or header pins. And so the places they would go would be the pin header connection on your circuit board. On this particular board, so I showed in our schematic earlier that we're going to need 3 points of connection. We need our positive signal line, our negative signal line, and ground. For DMX devices, it's often really useful to have another place where you can take some signals in and then jump them right off of this board out to another DMX object. So I'm going to use a 2x3 pin header. So I have a place for signals to come in and a place for signals to go out. Chris says, do you want to show the library manager for those not in use? I do want to talk about the library manager, but I'm going to do it when we get to talking about building your own components for your circuit boards. So to add a 2x3 pin header, I'm going to scroll down in our pinhead library here to pin HD 2x3. And as I spin this open, you'll see it's actually giving me 2 different options because it thinks we're adding a place to put one of these tall physical pin headers in place. Now, I'm going to leave those empty and solder wires into them, but it doesn't know that. It's giving me options for these vertical version and this right angle version that would, if you wanted a connection to come in from a side. The holes that they have are the same, but of course the place it's going to assume that it shows up on your circuit board will be different. It's going to tell you need to leave room for that right angle connection. So I'm going to use this vertical version because I really just want some holes in the board I can use for something later. So I'm going to hit OK. And now I've got this 2x3 pin header stuck to my cursor here. Let's drop that in the circuit board. And now let's look at connecting things. The command for connecting things in Eagle is the net command. It looks like this green right angle here, or you can type net into the command line, and that allows you to draw little green wires, basically nets is the technical term for them. That's how we represent an electrical connection in a schematic diagram. Just gonna undo all of that. So we will make an electrical connection from one part to another by clicking on a pin, on a connection on one of the parts in the schematic that we've already dropped, and then clicking somewhere else on our circuit board to continue placing that net. You'll see, and I'll zoom way in so you can see it, when you mouse over a point of connection on a part, you get this green circle. That's the editor telling you, hey, here's a place where you could attach a net to. So you see if I mouse over 7 or 6 or 1 or 2 or 3, all possible points of connection. So let's start by wiring our signal connections to our header here. So I'm going to click on my pin B here. I'm going to drag over and connect it to pin 1 on our input-output header. And then I'll connect connection A, I'll drag it over, but you'll see that since they're not in the same line, it's wanting to do some kind of an angle between them. You can change what kind of angle it gives you by default using this menu up at the top here. So right angles on schematic diagrams are pretty much the standard. You might have some good like artistic or layout reasons for using 45 degrees. You can also do curves, although I wouldn't necessarily recommend it, or freehands. I mostly just stick to right angles. You'll see it tries to guess which way the right angle should go. If you right-click your mouse, it will swap which way the angle is bending, which is handy. So I want this A wire to connect to pin 3 over here, but it'd be nice if it didn't overlap this point for pin 5. It's going to be a little bit confusing. So what I'm going to do is just drag out here and go up a click here. I'm going to click, that locks that point in place, and then I'm going to carry over my net to pin 3. I see I've got that little circle there, so I know this is going to be connected. I'm going to click, and you'll see when you've made a point of connection to a component, it takes the net off of your cursor. It's a good way of confirming that you actually have made that point of connection to the part that you thought. Chris asked a great question, which is lines that cross are by default not connected, and that is true. So, for example, let's say I needed A to be connected to pin 1 and B to pin 3 here. If I take these components and say connect B to pin 3, if I take A and give it a net and cross the streams here, as it were, these two nets right here are not connected. If I wanted them to be connected, which I don't, but if I did, I could use the junction command, which looks like a black plus with a green dot in the middle of it here, and click on their point of connection. And now it's actually going to say, hey, it's going to connect net segments. It's say, hey, these are two separate nets. Do you want to connect them? And if so, what do you want to call it? Now, as you make nets, it will automatically number them N1, N2, N3, and so on. And for most generic nets, you just don't necessarily care what they're named, although we'll see uses for naming nets in a little bit. But this is a way of verifying, like, hey, did you really need to connect these two things? And in this case, I don't. So I'm going to undo some of this and take us back to our original net connection with connection on B to 1, connection on A to 3 here. Let's see. Palmer asks a question, which Chris is, I'm sure, has already gotten. Are connections magnetic in that the lines would move the components removed? Yeah, So the move command, which I sort of hinted at earlier, it's these 4 arrows where you can type move in the command line. If you move a component, the nets will come with it, which is really, really handy. You can see, of course, that if you move a component, they don't necessarily move in right angles. They just sort of takes the last segment of the net and moves it along with the part. So things do stay connected. Often I find it's necessary to like move a part and then, for cleanliness sake, go through and delete some of these nets and remake them so things are a little cleaner. It's probably worth mentioning the delete command at this point. It's this trash can over here, or you can type delete in the command line. And once you have the delete command enabled, you can just go through and delete things. That's pretty straightforward. You can delete nets, you can delete parts, and so on. So that's the basics of using a net to connect multiple parts. Now let's say I had multiple parts that I wanted to connect to the same net. Like, for example, and my let's see here. My little Stream Deck is once again throwing up on me here. I think it's actually something to do with Windows, so maybe I'll restart that program in a second here. If you have multiple points that want to be connected to the same net, like, for example, I'd like both of that pin 1 there to be connected to the same thing, what you might do is something like this. So I want both of these points in this connector to be this B communication line here, because I want to use one as an input and one as an output, and they all have to be connected together. So I'm going to start my connection on pin 2 here, drag it up and out, and then when I click on this existing net, you'll see it makes a junction for me. Because it assumes that because I'm terminating a connection at that net, I want it to be connected. I could take this connection here and terminate it right at this other pin. This is not great practice because it's a little bit easy to miss that this connection is being made. For something like a pin header like this, where connecting two things side by side is, fairly standard, it's okay. But it's always going to be cleaner to actually drag your connection out and make it somewhere else. And I mean, again, we can see that junction dot there that tells us that those two things are connected. Palmer asked an off-topic question. Do I have an actual Stream Deck? No, I'm using the Stream Deck app on my phone, which was like a 30-day free trial and $3 a month, and it works pretty well. It's a little janky with Windows. Bonjour keeps crashing, but that's, I think, a Windows problem and not a Stream Deck problem. But that's a fair question. So we've done 2 of the 3 kinds of connection on this header pin here. We'll remember from our schematic that we need 2 points of connection and we need a ground connection on it to ground that signal. Basically, that'll be attached to the shield of our signal line so that things are nicely grounded at both ends, or really on one end we should do, but that's beside the point tonight. So we have a special way of adding ground connections in our circuit. Now we have some ground pins for our IC up here, which are meant to be connected to ground, and it tells us so. So we could, we could drag a net from here over to this ground connection here, but we actually have a cleaner way to do this. Much like in the Jeff CAD version of this circuit, I have these ground symbols here that say, hey, any of this point is connected to this kind of like triangular symbol is connected to ground. We can do the same thing in our circuit diagram by adding a ground part. So we'll go back into our add command, and if we go to the supply 1 or supply 2 libraries, which are really identical, they just have slightly different styles to them. If we come down to this GND part, that will be a ground supply symbol. You can also see there's analog ground, ground I, ground int, and so on. These are meant for if you have circuits that like need different ground planes because you have sensitive parts that can't share a ground with something else. But we're just going to use our basic ground part. So, and that's going to attach to my cursor here like any other part would. I'm going to bring that down and drop it somewhere below our header block here. And then I'm going to use my net command to tie that in to pins 5 and pin 6. And I'm going to be a good boy and not connect. You'll see, so I made it's asking me if I want to merge net N4 into supply net ground. So when I attached this network here to this ground part, it automatically named this net ground, which is what we want. Like this is now this set of connections, anything connected here is connected to ground. And in a similar way, I'm going to connect my ground pin up here to ground. So I could go back into the add command and add another one, but we can shortcut a little bit by using the copy command. Looks like 2 pieces of paper over here. If I use the copy command and I copy my ground part, then I can simply place another ground part up near my power pins. And once again, I'll use the net command to connect those 2 things in. So now I have my ground pin wired in there. And while we're at it, why don't we hook up our power pin? Much like there are ground supply symbols in the standard libraries, there are power supply pins. Which one you use is sort of a matter of choice. There is sort of a 5-volt supply pin. I typically use this VCC pin here. It's really just a matter of like what you want to do with your circuit diagram. Just know that like any you connect to this any plus 5 volt symbol, for example, on your circuit board will be connected to all other plus 5 volt symbols. All other VCC symbols will connect to all other VCC symbols, but they won't necessarily be connected to each other, if that makes sense. So as long as you sort of pick one and stick with it, you'll be just fine. So I'm going to add a VCC pin symbol here up at the top. You see it's labeled itself VCC. I'm going to use my net command to tie that to my power pin. And now that'll tell that wherever my VCC, my power is, I want to tie pin 8 of IC1, the power pin, to that power network. Cool? Questions so far? I need to take a moment and drink a bit of beer, and I realize I should mute my mic while I do it, because now that the mic is right here, it's probably a real in-depth ASMR experience for y'all. So if you have questions, now's a good time to ask them as I hydrate just a little. Hydrate. I don't know what the name Snick 1 comes from, but it's a really good beer. Beguile is really local to us. I need like a mute button. All right. Well, if you have questions, as always, ask them. Thank you for the pause. Hydration is good. Chris mentioned earlier he might be playing along in Fusion 360 tonight. I'm doing the Eagle version. That's super cool. Yeah, Chris, keep us posted on like anything that is or isn't possible, because in theory everything is possible. We maybe will do I don't know that it counts as electronics bash, but we could do a Fusion 360 night where we like build some 3D printed designs at some point. That'd be kind of fun, because it's all a rabbit hole from here on out. So who knows? But yeah, Chris, keep us posted on how things go on the Fusion 360 side of things, because that's a super cool possibility. I'm gonna check my outline here that I made, because I got all fancy tonight. We added our ground connector. We've looked at copy and paste. Let's look at something else. So I think I'm gonna need a little bit more space up here to do some circuiting layer. I'd like to move these parts out of the way. If I just use the move command, you'll see it only lets me move one part at a time, which is kind of obnoxious, we can use the group command to make our lives a little easier. Now, the group command doesn't work like group does, say, in Microsoft Word or PowerPoint, something you might be used to. It doesn't create a group of objects that you can then later ungroup to do things. It creates a temporary association between those objects for basically the next set of actions you take until you use the group command again. So let me show you what I mean. The group command, which one? I don't actually know what the group command looks like. I just type it in whenever I choose to use it. Group command must be one of these. Pattern, paint roller, must be one of these up here. Invoke. I don't know where group is. Where are you, group? My little toolbox keeps going away as well. Reposition, edit 3D. Well, I'm just going to type group into the command line and save us this monkeying around. If I type group, then I can click and drag a box around a set of components. That will define a group around them. Or if I have the group command active, I can click single points, and that will let me start defining a polygon around sets of components. And then I can right-click to close the polygon off. And you can see these parts have sort of highlighted themselves in a brighter color to let me know they're grouped. To move them as one, I'm going to activate the move command. And you see it tells me down at the bottom here, control right-click to move. I'm going to control right-click, and then I can move that group of objects as one, say to get them out of the way over here. Grouping and moving, or grouping and deleting, is really a useful thing. You can group and copy, you can group and paste, a useful way of moving things around together. Let's see. Oh, Nate asked about pricing on Fusion 360. So the hobbyist version is still free. If you make less than a certain amount off of your projects a year or off of your business, the hobbyist version is free. Above that, they expect you to pay for a license because you're a small business. But the last time I checked, the limit was like $100,000 a year in profit. They really only care if you're making, big money off of your projects. Which if you have that problem, good on you. That is awesome. But for free, for hobbyist level uses in small businesses, no, the license is totally free. In the newest version of the license structure, I want to say they've taken away some of the like CAD CAM capabilities, like the maybe the sheet metal is now a paid feature. Basically, the things that relate to like CNC milling and machining have gone away or gone into a more paid version as of like last year. I don't really use those features, so I don't know all the details, but that might be something to look into, is what those things. It used to be just like free, had all the features until you made enough money, and now they've gone to kind of a tiered model where they have locked a few things away. Let's see. We've done our ground. We've done our VCC. Oh, so let's continue building out our schematic. So let's add our attachment points for our Arduino Pro Mini over here. So our Arduino Pro Mini has 12 pins down each side here. So 12 on that side and 12 on that side, separated by a specific spacing. So when we lay out our circuit board, we'll need to get that spacing right. But for right now, we're just going to add two 12-pin headers to our board. And since they just show up on our circuit board as holes, it doesn't know that we're going to, choose to solder in a female header to snap our Arduino Pro Mini into rather than a male pin. It's just going to put a row of 12 holes there, which is what we want. So let's go back into our add command. We will go to our pin head library again. I'll come down to 1 by 12. And again, I'm going to use the vertical version here instead of the 90-degree version, just because I just want a row of holes. And we'll want two of them, 1 and 2. And that's going to be the places where our Arduino Pro Mini attaches to. I am going to, first of all, make sure that this Arduino is going to be hooked up to power and ground. And though this is not electrically necessary, I am going to lay out the headers on my schematic in the same orientation that my headers on my physical device are, just because that's going to make things a little bit easier to for me to like grok and understand and check things later. You could, they could be 90 degrees. Those headers could be far apart from each other. Electrically, it's the same thing, but like maintaining order and sensibility in your circuit diagrams is sort of just as important as making them electrically correct. And this I think I alluded to earlier, I put some cheat diagrams in the slides here so I could remember what pins were connected where. So I'm going to start by doing a power and ground pin. So much like before, I'm going to create a couple of nets here, and I'm going to copy my ground symbol over next to the ground pin and copy my VCC pin symbol over to VCC. Now I think for this circuit board, I'm going to use the Arduino to power the Max 485 chip rather than putting external power on it. So what I actually should do is delete that net, and I should hook up the power pin to the 5-volt line, which is, I think, pin 4 on this side. Yeah. So let's use the move command. We'll move this ground pin out of the way. We'll move this net over. Oop, net. And we'll net that pin to ground. And it'll ask me again, this net, which I didn't know was a thing before, do you want to make it a part of the ground network? Yeah, I do. Thanks for checking, Eagle. And then I'm going to move my supply pin here down over. I'm going to connect it to pin 4. So that's going to supply 5 volts from the Arduino to this VCC, this power network, which we know is connected to pin 8 of our Max 485. So I'm going to use the Arduino to power that DMX transceiver. So there's those two connections. Now let's route the data connections between the Max 485 and the Arduino. And I've chosen to use, I need to use pins 0 and 1 for transmit and receive because of the way that the hardware on the Arduino is wired. I have a choice of what digital pin to use for the control pins, kind of control the directionality, whether we're transmitting or receiving. I'm just going to, I'm already using pins D1 and D0 and D1 for transmit and receive. I'm going to use pin D2 as my control pin. It'll be totally fine. So I'm going to net pin, the receive data here is going to come up and over and go into, I'm going to double check on my diagram here. Yeah, going to come up and over into pin 2. And then the transmit data here is going to come up and over into pin 1, and then pin D2 is going to come up and over. It's actually going to connect to both of the receive enable and the transmit enable pin here. This is a thing we talked about last week, and you can sort of see in the symbol here, we have DE and RE/. So DE is the transmit enable pin, and if we didn't know this, we could find out in the datasheet. In fact, let's look at the datasheet. We can see in our datasheet here, sorry for the scrolling, we come down here, pin DE, pin 3, is our driver output enable pin. Driver outputs Y and Z are enabled by bring DE high. The receive enable pin, receive is enabled when RE is low. So by tying them together, we can actually determine whether we're transmitting or receiving using just the one pin. If this connection, if this pin, this digital pin on our Arduino is low, we'll be in receive mode because receive is active low. If it's high, we're in transmit mode because the transmit enable is active high. When you see this slash or you see this over bar, in say a data sheet, that's, as I think we talked about last week, that implies that things are active low. By default, we think of things being high, things being at 5 volts, is on, is go, is good. If you see that bar, it means it's active low. So 0 volts or off is actually things are functioning. And they do that for good reasons. In this case, it's specifically so you can use a single digital pin from your controller to control whether the thing is in transmit or receive, because you'd rarely want to be doing both of those at once, if that makes sense. So these are our data connections to the Arduino, and this is fine. I think this is a little bit messy, though. It's a little bit hard to see what's going on here. So let's look at a slightly different way of making these connections that I think is going to make things a little bit cleaner. So I am going to, I guess I won't undo all of them. I'm just going to delete them as we go. In fact, let's undo all that. We'll take all that back. I'll show you a cleaner way to do this. First, I'm going to use the group command and the move command. I'm going to control right click and just move this header out of the way a little bit so we have a little bit of room. I'm going to create just some nets that go nowhere off of our various pins here. We'll still want our receive enable and our transmit enable to be connected to each other here. That's fine. And I'm going to create some nets that go nowhere off of pins 1, 2, and 3 over here. I'll make this one a little bit long. We'll see why in a second here. What I'm going to use now is a command we haven't used yet called the name command. It's this tool over here that is a bold R2 over 10K. When I use the name command and I click on a net, it's going to say, hey, Okay, what do you want to name that net? It's, like I said before, it's automatically naming our nets N1 and 2 and 3 because it assumes we don't care what they're called. It's going to use an internal placeholder name. But if I choose to give them a name, then any nets with the same name are going to be connected. So, for example, if I name this net, let's say receive, let's say RX, you'll see it actually gives me an option here to place a label for that net. It's like, hey, if you're naming this, do you want to put a label on your diagram what it's called? Sure. When I say place a label, and you'll see it connects this little RX symbol to my cursor here. You can zoom in and see a little better. Now, this is all well and good. I actually like this style of label called an XREF. If I turn that on, it gives me this nice arrow label because that's pretty classy. And if I right-click, it'll rotate around my point here. So I'm going to say that's going to be the net labeled RX. And then if I come over to my my Arduino connection header over here, and I'm just going to double check which pin it is, TX RX, yeah, be pin 2 here. If I name this network also to RX, it's once again like before when I was connecting two physical nets on the network. It'd say, hey, do you really want these two things to be connected? If I say yes and place another label, now it knows that this RX net and this RX net are connected. I don't have to deal with this mess of wires going back and forth between the two. So let's do the same thing with the other 3 connections we need here. So we need a transmission data network. And again, I'm going to place a label there. I'm going to call this one the same thing. I'm going to call that TX. And again, I'm going to confirm that those things are connected to each other. And I'm going to need a direction control net. Let's call that the DIR net. These the network names are really just for you. Like, they're not going to show up on your circuit board anywhere. They may be helpful to you in circuit board layout later, so giving them evocative but short names is a good practice to get into. Nate asks, are we having another Jeff Glass 90 minutes? Definitely. Nate, I don't know how far through the backlog you've made it. None of these have ever been a true 90 minutes. Someday. So maybe when I'm actually back at, my full-time job I will have to cut them down to a slightly shorter topics, but we're gonna go tonight. But we're making good progress, I think. I think this is good and meaty and I think useful. So now we've made our data connections here to our Arduino header over here. So we have a couple more parts to add, right? If we go back to, there we are. That's like the first time in like a couple episodes I've done that. We're doing all right over here. If we come back to our schematic, we'll remember that we had a couple more parts to add, namely these resistors that I said I would explain later. But let's go ahead and start laying out our board, and I can show you the interplay of going back and forth between the board layout manager and the schematic editor. So in our schematic here, which before I forget, I should save, we'll call this demo schematic. If I have not yet created a circuit board for this, then the first time I go into board mode, which I can do by coming up to the top here and clicking this SCHBRD button, that switches you back and forth between the schematic editor portion and the board editor function. If I click this, it's going to say, you don't have a board for this yet. Should I create from the schematic? Yeah, that sounds great. So I click yes, and you'll see it populates here with a screen. This is a default board size that it's laid out here. This sort of shaded black area is the area that makes up our circuit board. Everything outside of it is no man's land. Anything we don't put inside this black area, we're not going to get manufactured. And it's gone and dumped the footprints for our parts into no man's land out here, ready for us to move them into the outlines of our circuit board. So let's go ahead and do that. I can use the move command in the board editor just like I did in the schematic editor. I'm going to zoom in a little bit here. I've got jumper 2 and jumper 3. And if I go back to the schematic editor, just double check. So jumper 3 I said was going to be on the left here. So I'm going to activate my move command. I'm going to click on jumper 3. We can say I can move it around with the mouse. And just like I did with the label, as I'm moving something, I can right click to rotate it. So we'll rotate this around until it's, approximately right side up from how I'm imagining things here, and in the same orientation as it is in the schematic layout. And then I'm going to move my other header here, jumper 2, over onto the board. So I'm going to want to make sure that the spacing of these, of course, matches my actual Pro Mini here, which I looked up in advance is 600 mil or 0.6 inches. So how are we going to make sure that our dimensions on our board layout exactly match that? We can make use of the grid. So In Eagle and all PCB layout programs, things by default will snap to a grid. And it's actually really good circuit layout practice to keep things on a grid. It keeps things predictable and makes them visually nicely laid out. If you're hand assembling things, it lets you sort of easily work through a workflow if things snap to a grid. A sort of default practice is to keep things snapped to a 100 mil or 0.1 inch grid. If you come up here to this grid icon, this sort of like giant tic-tac-toe board, and click on it, you can define the size of your grid. We can see here I have my default grid size set to 50 mil. Let's set that to 100 mil. So as things move along, they're going to snap to increments of 100 mil. You can also define an alt grid size, and it's literally when you hold down the alt key while you're moving something around, it will then snap to increments of the smaller grid. So let's say my alt side I'll set to 50 mil, set to half as big. You can choose whether to display the grid or not. You see if I set it to display, it actually displays it on my diagram here. I typically leave the grid display off, but it can be useful if you're really getting into the nitty-gritty of layout. So let's make sure that our two jumpers are separated by 600 mil by moving jumper 2 over the first and then going over 1, 2, 3, 4, 5, 6. So 6 grid spaces at 100 mil each, so I know these are separated by 600 mil. If I wanted to, I could turn my grid display on and verify using my grid lines. Yes, those are exactly 600 mil apart. So that's going to be the footprint of where my Arduino Pro Mini snaps in later. You can see that's going to end up being these 2 rows of holes down the outside here where that Pro Mini is going to ultimately end up getting soldered in place. So let's drag our other components over onto the board for now. Let's take our header connection here, and let's drop that in somewhere down here, but I'd really like it to be kind of centered between these 2 sets of headers out here. So I'm going to hold down Alt, and that's going to let me drag not by 100 mil, but by my alternate grid size of 50 mil. Get that nice and centered between those 2. Ooh, doesn't that feel good? It's nice and symmetrical there. And then I'll drag my Max 485 footprint over here into the board as well. I think I'm going to want it to end up being in this orientation, and here's why. These yellow lines here, and we'll look at them in more detail in a second here, are what's called air wires. Those represent the electrical connections that your pads are ultimately going to have to make. Now you can see, because they don't represent any actual copper at the moment, as I drag a part around, they just follow behind the part, but they're there to let you know, hey, you know, if I zoom in here, this pad here and that pad there will ultimately need to be connected to each other. And so they're a good visual guideline for hey, what orientation makes sense for this part to be in. And as I right click here to spin them around, you can see like this orientation where, you know, things from my header are going to have to cross up above here. That's not great. That's a little better. Actually, this orientation looks really nice. I think I'm going to do that. Let's do that orientation. And again, I'm going to use my Alt, make sure that's nice and centered. Actually, my main grid gets me pretty centered there. You actually saw a thing there that I did by accident as well, which is that if you right-click with your mouse, you rotate your device, 90 degrees each time. If you middle-click, you do what's called flipping the part, which is basically mirroring it 180 degrees and putting it on the other layer. So right now, I'm working on my top layer, which in Eagle, the default color is red. Layer 1 is our top layer. That's literally going to be the top layer of copper on our PCB here. If I wanted to put this part on the bottom layer here, and because it's a surface mount part, right, it's only going to go either on the top or on the bottom and not both. What I could do is select that part, move it around. If I click on my middle mouse button, it flips it over and puts it on the bottom. So now that part exists on the bottom of my circuit board, and now it exists on the top. Crucially, it's good to remember, so that is the bottom of the circuit board as viewed from the top. So it's not that I'm looking at the board from the bottom, I'm looking through my board at those individual layers. And you can see why that would make sense if we were doing 4 or 6 layers. We wouldn't try to figure out what orientation we would be. We basically have X-ray vision all through all of our copper layers down to see our various layers of the board. So I'm going to leave this one on the top for now, but we may make use of that bottom layer for something else later. I need another quick hydration break because we're going hot and heavy here. But so forgive me as I sip my tasty Snick 3 from Beguile Brewing in Chicago. Delicious. So now that we've placed our parts here and we've looked a little bit at air wires, one other command that I want to introduce now before we go back and add our resistors into place is the rat's nest command. That is, if I can remember what it is, that is this command that's 5 circles with lines between them, or as always, you can type the command rat's nest into your command line here. Rat's nest basically says, hey, redo my air wires so they're actually, form the shortest paths between connected parts. So let's say, just for sake of argument, if I move my command out here, I have a few networks like my ground network that have multiple points of connection. I have a ground pad here, I have a ground pad on this device, and I have a ground pad on my headers down here. And you can see, because I named those networks, this is telling me that I had this net here is telling me this is a ground pin. I'm also seeing that this is connected to net N2 and N1 and so on. But any nets that we've named, the names for those nets will show up in the pins here, which is pretty handy when you're trying to figure out what goes where. But when you start moving parts around, the air wires just sort of blindly follow and come along with you until you do the rat's nest command. And that makes those air wires follow the shortest possible path between related pads. So just a useful thing as you're moving parts around, you can do a rat's nest and say, hey, make my air wire sort of as cromulent as possible and not sort of silly looking, if that sort of makes sense. So let's go back and add our final 2 components to the board, those couple of resistors, or our final 2 passive components, and then I introduce a component that we're going to need to build after that. So I'm going to come back to my board, and I'm going to add these 2 resistors that I promised to explain. These are basically a pull down and a pull up resistor, which we've talked about in previous situations where we've looked at analog and digital input. For RS-485, for DMX to be reliable, we need to basically have this transceiver be in a state where even if there's not something driving these lines, we want this receiver to always be in a defined state. We want to say like, hey, if nothing else is controlling these, I want B to be low and A to be high. So I'm going to put a high value resistor from B to ground, so gently pulling that line to ground like a pull down resistor. And I want a resistor that's going to gently pull this A line to positive 5 volts, so it's always sort of gently pulled to high. Now, if we drive this with a DMX transmitter, we're going to be able to sort of overrule those values on this line very easily. But if there's nothing driving this line, we don't want things to sort of be floating and ambiguous. So let's add those 2 resistors now. Resistors, we'll go into our board editor here. We'll come back to our schematic editor. We'll hit SCH here, back over here. We'll use our add command again. And most passive components, so resistors, capacitors, etc., live in the RCL library here. So we'll open that up. I'm going to come down to, I've got C, US, C, European symbol, various other things, L for EU symbols. The Europeans and us use slightly different symbols for these various things, so they're broken out into different libraries. I'm going to come down to US resistor symbols, and you'll see they're all broken out by the various packages that they exist in, the various through-hole and surface mount packages that these could be. I'm going to make use of some little tiny surface mount parts here, specifically an 0603, which we talked about surface mount parts and their sizes last week. So this is 60 mil by 30 mil. For size reference, that's going to be these 3 little pads, and are actually 3 resistors in the final version of this board. So I'm going to make a resistor R1 and R2 to be those pull up and pull down resistors on my board. So I've got my part here, my US resistor 0603. I can click add or double click it and add it to my board. So I'm going to want a pull down resistor somewhere in here, and to play a pull-up resistor somewhere in here. I'm going to want to connect them per my Jeff CAD schematic over here to 5 volts and ground. So I'm just going to duplicate with the copy command my VCC symbol, drag that over there, pull my ground symbol down over here. And it's not good form to have your ground symbol. Like, I could put the ground symbol there, but it's considered better form to give yourself a little space so you can see the visible net between them, so you can verify that they're connected. And then I'll just net those that resistor into the A network, that into the B network, and so on. So now I have a resistor between 5 volts and this line, and ground and this line. Now, I haven't shown anywhere on the schematic what value those resistors should be. For our purposes, they're going to be about 1.5 kilo ohms, and there is a way of specifying what that value should be with the value command. It's next to the name command. It's got a gray R2 and a bold 10K. It's going to be our value command, and if I use the value command and click on a component, it asks me for the value of that component. I will say 1.5K, and you'll see it shows up on the schematic here. And similarly, I'll do that for our other resistor, 1.5K. Now, of course, we're just making a circuit board, right? We're not necessarily going to stuff it with components until after it's manufactured. So this value may be just for our reference, or maybe with reference for the factory that's going to be machine assembling these things for us. But it's good practice, especially when you have passive components like this that could have a lot of different values, to put values for your components in your schematic like this. Yeah? So those are the two resistors I'm going to add for now. I'm going to go ahead and go back to my board editor, like CircuitBoard over here. I'm going to use the move commands to now move these two resistors into place. And now we can really see the value of those air wires telling me that, okay, I'm going to connect this resistor is going to be connected to this pair of pins over here. Well, that resistor probably needs to go right about there. And this resistor is going to be connected to that pair of pins, but I can't quite tell how it's going to connect. So I'm going to run a rat's nest command, and that's going to cromulinize, if that's a word, my air wires and tell me a little bit more about where they go. See if that makes choosing where these things are laid out any easier. And we can see with how those air wires are laying out that this seems like a good place for it. So that seems like a good place to be. Now that I sort of I have the bulk of my components, although I did promise there's one more to add, I'm going to go back to Palmer's question and define the size of my circuit board by moving its edges. So I'm going to use the move command on these yellow outline lines and just move them over closer to my board. Move that one down, and so on. So when I send this file ultimately to a manufacturer, and we'll do that later tonight in the second 45 minutes of this evening. This might be a long one, y'all, but we're making good progress. They're going to manufacture my board to the size of my outline layer here and no bigger. If you want to have an outline that is not rectangular, well, you could make it trapezoidal by just moving things sort of out of plumb there, as it were. But you have a few other options that you could use to make things a little bit more interesting. You can use the miter command, which I believe looks like this. It's got a sort of a corner taken out of it on a corner. And if you select a new radius, let's say 50 mil, and click on a corner of your outline, you'll see it chops away the corner of your outline for you there. If you choose a different, so this is currently in straight miter style. If you use round miter style and click on a corner, it will round that edge off for you. And we could say, well, maybe that's nice, but maybe I want it to be 100 mil. That's going to round the edges of our circuit board for us there. So if you need rounded edges, or if that makes, if you're slotting this thing into a slot and having rounded edges to make it slide in easier, using the miter command, for example, can be really useful. If you wanted to do a more exotic shape like the board that I showed earlier, this guy, which I had a very specific reason, this needed to connect to a big fat connector out here and then slot into a project this way, you can use the line command to create additional lines on the dimension layer of your board. So use the line command to come down to dimension. You'll choose a width of 0, if it'll let you, and then you'll draw, basically. So I'm going to delete this top line, say, right? And now it doesn't know where my board starts and ends, so it sort of filled in the entire universe with, hey, I'm going to manufacture this. I'm going to use this line command on the dimension layer to draw the new outline of whatever I want my board to be. Now, it can be a little bit tricky to get things to line up specifically, but you do want these lines to line up as nicely as you can. So I'm going to decrease my alt grid size to get things to line up nicely here. Ooh, still not wanting to. Let's see. If you're going to redo this, I guess the best advice I have is to go ahead and delete your whole board outline and draw it from scratch, because this happens to me almost every time with these board outlines, is they don't want to line up nicely with things that I just moved in from another layer. Let's see if I can get this to line up. Doesn't seem like it. Maybe I'll just redraw it from scratch here. Oops, there we go. So I'm going to delete my board outlines on a bit of a tangent now, but I think it's kind of interesting to be able to make multi-shaped PCBs. So I'm going to re-enable my alt grid here to be, I don't know, 25 mil, just so I have a little bit better control. Come up here, no miter, no miter. There we go. And we can draw our board outline. And when it snaps back to being closed, you can see now it knows that this inner area is the shape of my circuit board because it's grayed out everything out. It's made its no man's land again. So if you're looking to make dimensional circuit boards of interesting dimensions, drawing lines on the dimension layer is the way to go. I'm just going to go back and undo all that so we have our nice rectangular circuit board again. And you'll see it doesn't always, as you're undoing things especially, it doesn't always update this no man's land accurately. That's fine. When you output the file, it will figure it out. Or I think if you go back to the schematic editor, it'll sometimes update it for you. But that'll take care of itself in a second here. So sorry, a little diversion into talking about board outlines there. So let us take a quick look at the process of routing your connections, and that's the process of defining where the traces on your circuit board are going to go. It's the process of routing them through your board. Then we're going to take a quick diversion to making your own parts. We'll route that part in, and then we'll look at manufacturing your board. And that will take, I'm sure, only 10 minutes. So here's how routing works using the route airwire command, which is this command down here with the little blue wire on it. What we'll do is we'll click on that and we'll see we get a set of new tools. We're currently drawing this routing on our top layer of copper here. It's asking us to tell it how wide our trace should be in mil. Like I say, there is not necessarily a standard trace width. For a small signal, something like 12 mil is fine, I think. Most manufacturers will go down as small as, say, 8 mil, or 6 mil is like the smallest trace they will route. For small amounts of power, this is really like all you need. When I have questions, and Palm, you sort of referenced earlier, how far apart should traces be before you start worrying about voltage between them, or how high can voltage be before you start worrying about trace separation. I am often more worried about trace current, and whenever I Google trace width calculator and click on this great tool from 4PCB, which basically says, there isn't like if you want to carry X amps, your trace has to be this size. It's if your trace wants to carry X amps and rise by no more than Y degrees, here's how big it should be. So we'll take our inputs here. Let's say I want our trace to carry, for a digital signal, maybe 10 milliamps at max. That's really generous. We're going to work on this 1 ounce copper, right? That'll be sort of our default. We talked about copper thickness a little bit earlier. Let's say I want that trace to rise by no more than 10 degrees C. Room temperature is 25 degrees C. That's fine. And my trace, well, and it can be no more than 1 inch. This says if my trace was 0.05 mils wide, I would still be fine. So that's 5, 10, 100 thousandths of an inch. So if we go to 12 mil, we will be totally fine. Now you can see if I mess around with the parameters here, I'm going to zoom in a little bit. If I say I want my trace to carry 1 amp, and rise by no more than 10 degrees C, I need a 30 mil trace on 1 ounce copper, and so on. And actually, the information is different whether we're talking about an internal layer, right, which is going to have a harder time getting rid of heat, than an external layer, which is going to be able to sort of free in the air. So 1 amp at 1 ounce copper is still a 12 mil trace. So using a 12 mil trace for a signal line that's going to carry hardly any power is going to be more than plenty. But defaulting at 12, a nice generous size. Any board house should be fine with it. Should be totally good. So let's route a connection, let's say between these 2 pins on our header here, that should both be ground, should both be, the A signal and the B signal. And we know they should be connected because they have this yellow air wire between them. So I route that connection by clicking on one pad, and you'll see it highlights all of the pads that should be connected to. So if I click on, say, this N1 pad, drag it up here, you'll see for some reason it's already switched me to routing on the bottom layer here. I'm going to come back to, if it'll let me, route on the top layer, right? I'm going to click on one, and when I click on the next pad, it will complete a connection between the two. And now I have a trace between these 2 pads. I'll do the same for my B signal pads. I'm going to leave my ground line aside for a little bit, and I'll show you why in just a little moment here. But I'm basically going to use this trace tool to, this route airwire tool to continue laying out the various traces that I want to see on my board, using my grid and my alt grid to keep things nice and tidy. So in terms of, you can see I'm making use of this setting up here that's routing everything at a 45-degree angle. This is not... Okay, so here's the truth about 45-degree angles and traces. For a long time, it was canonical knowledge that you never wanted traces or pads or components to meet at less than, say, a 45-degree angle because, as we talked about earlier, when we're creating these copper layers, the acid from your, you basically coat the whole thing in copper, and you have to get some acid down into very small areas of your board to etch away the copper you don't want. And if you had too acute of an angle, the acid might get stuck in one of those corners and eat away too much copper and eat through your trace, and your circuit board would fail. It used to be that like 90-degree angles at things meeting is that's awful, can't do. These days, manufacturing has gotten really good. It's mostly fine. A 90-degree angle junction is fine. Anything less than that, like an actual 45-degree angle, like a 135-degree joint, is not necessarily great, but will probably be fine. In any case, it's good practice to keep your joints to either a 90-degree angle or a 45-degree junction. If you have two traces coming together so that they make this like nice acute angle down here, it's good to sort of split them apart so they meet at a 90-degree angle. If that makes sense, prevents you from ever having to worry about that sort of acid catchment. So now for this process of routing, I'm really just going to take all of my traces and following my air wires, I'm going to connect all the various components that are connected by air wires here. I've got my VCC terminal, going to connect to my 5-volt pin on my Arduino. We can see, here's one of my very narrow angles down here. I want to avoid this because in manufacturing, you might get some etching acid stuck down in there. So let me undo that. I'm going to use this to bring my trace out horizontally at a 90-degree angle to my pad, and then I can continue bring it up to my other pad here. And I'll just route real quick, in a more complicated board, you might need to think in a more detailed way about like where your pads were going and how. One useful trick, so we can see like I have this pad and this pad with these two air wires sort of going up straight and this pad crossing over them. You can route traces between pads of your devices, especially if they're big chunky through-hole pads like this. So I'm going to take my trace in between those two pads, and that kind of gets it out of the way. Oh, and these two actually are tied together, so that makes that easier. Bring that up and out here. That's my direction connection. And here's my RX connection. That's going to come up here like so. And what's this? Ground connection. Have we got anything else? So when you get to the point of asking if you have any further connections, and I swear I'm going to deal with this ground connection here, you can do what's called a design rule check, or a DRC. When you use this DRC check here, it's going to bring you into a display which asks you to define all of these minimum clearance, minimum size rules that I've been talking about all night. How thick are your layers? What's the minimum clearance allowed between a wire and a wire and a pad and a pad, and so on. Distances from copper to holes. How big a hole can we hide? What's our minimum trace width, and so on. Eagle's default design rules are pretty good, and I'll show you when we get to the manufacturing stage how to find manufacturing rules for your specific manufacturer, because of course this is really saying like, hey, can my manufacturer put two wires 6 millimeters from each other and still have them not blur into each other? And 6 millimeters is like, let's remember, tiny. Like that is the distance between the center of that of that copper pad and that copper pad. For two adjacent signals. Is that something your manufacturer can do? A lot of them can, some of them cannot, and so you'll just want to match your options to what they have. So that's most of what a design rule check is checking those rules. But if you will also check for things like routing errors. So we see when I run this design rule check, I get this errors list, and it's telling me I have 4 air wires remaining, 4 things I haven't routed. And as I click on them, it will highlight them for me and say, hey, there should be a trace there. There should be a trace here. There should be a trace there. There should be a trace here. Now, those are my 4 ground trace connections. So thankfully, I'm going to fix those for you in a second with a fill. But this is a good way of checking. Once you think you've routed everything, you run a design rule check and it'll say, ooh, you didn't route that signal there. You didn't route this thing. And you can go through and fix it. And as you do, it will eliminate these air wire connections. So let's say I was missing a trace over here. And by the way, I don't think I mentioned the way you remove a trace is not with the delete tool. It's actually with the rip up tool, which looks like 2 dots with an X in the middle here. Let's rip up this little bit of trace here so that there's an air wire there and run our design rule check again. DRC, run a check, and I'll see now I have 5 air wires, including this one. I can say, oh, I deleted that earlier. I shouldn't have. Let's route that back in. Route that in there. Now that air wire goes away. In fact, if I do this, let me undo that. If I do this with the DRC active, leave that up there. Let's highlight that. I actually leave that DRC up while I'm routing this trace, and you'll see as I do, it disappears, which is really handy. So you can just move through all of your various errors. DRC will also show you if you have other kinds of errors like clearance errors. So just to mess things up for a second, I'm going to move. How can I? Let's see if it'll let me do this. If I move these 2 parts on top of each other and these traces intersect, if I run a DRC and check it, it'll say I have air wire errors. I also have clearance errors because my traces overlap, and I have overlap errors. Right, it's all of this is not good. So we'll undo that and take it back to where it was. But the DRC basically says, hey, are you following the rules as you're laying these things out? I should also say, as I'm looking here, that this RX trace is kind of jutting out in a weird way from this pad. You can use the move command on traces just like you would for parts. You can move their junctions around to make them a little bit more cromulent, if that's easier than ripping something up and rerouting it. So that is the gist of routing. The routing tool, just like the wire tool, lets you define your wire junctions. Though we are only going to be having pads on one side of our board for this project, you can route traces on both sides. You can either draw traces, say, on your top or bottom layer, and now when you start routing something like this ground, it'll now route a trace on the blue bottom layer here. You can also move traces between layers using vias, which you remember when we talked about is basically a column that takes a signal or a bit of power between 2 layers of your board. And all you do is say start. Let's say I promise I'm going to deal with these ground signals in a second here, but just to use them as an example, let's say this ground line needs to start on the top layer and then jump to the bottom layer. If I start routing it on the top layer here, then just while I'm mid-route, come up to my layer selection, change it to the bottom. It's going to give me this green via that I now get to place. So I'll place that, say, there. And now, as I continue routing, it'll route me a bottom layer trace, right? And if you had multiple layers, it would let you define, blind or buried vias if you wanted to as well. But that's how you jump signals between layers, is you basically route them, change your layer, and it'll give you an opportunity to place that via for you. You can also, if you ever need to, there is a via command to manually place vias between layers, but most of the time you're just going to end up changing those layers as you're routing something. Chris asked a good question, which is why rip up instead of delete. The gist of it is delete would be removing an electrical connection between things, like deleting an air wire, which is not what we want. We want to rip up the representation of that electrical connection that our trace is, not delete the electrical connection. In fact, if you try and delete, say, an air wire, I don't think it'll let you. Yeah, it'll say, so cannot back annotate this operation. Please do this in the schematic. I'm saying, hey, if you really want to, make this electrical connection not a thing, do it in the schematic view, and then I'll let you, then it will no longer be true in your board outline view, if that makes sense. So we have the gist of our board routed here. I do want to show you, though, how to, if you have a part that's not in the standard parts library, how you make it in your PCB manufacturing process. Because this is, really a part of any PCB you're going to make. You're probably going to end up needing to design your own part, even for a little board like this. Let me show you the part that I had to make for this PCB, and I'll show you on the assembled version. So I mentioned, I think in passing, that the Max 485 had to be hooked up to the transmit and receive to digital 1 and digital 0 on our Arduino, which are the same pins, by the way, that we use for our serial connection to our computer. And that's because the library that allows for DMX connection via an Arduino sort of abuses some built-in serial hardware in the Arduino to make it possible to read those signals. The problem is, though, that if you are using those signals to say, transmit DMX, or receive DMX, that actually, that data is going to be on those same lines that we would use to either talk to the Arduino or to program it. And so it's really obnoxious that if you have DMX signal, say, coming in from a big fat connector coming into your Arduino, you can't program it without unplugging the DMX. So there's no signal on that line, and then it's not interfering with the serial communication. So what I did is introduce this little switch here, that basically, either in the enable mode, the lines are connected to the Arduino, and in the program mode, they're just disconnected. Like, I can either sort of connect those data lines to the Arduino and let the DMX flow through, or just hard disconnect them, and then I don't have to worry about it. But of course, this little switch, which is adorable, is not a standard part. It's something I found on DigiKey and ordered a bunch of, and then just needed to make a part for so I could put it on my circuit board. So let's look at how you make a part in the Eagle libraries to add to your circuit board. And by let's, I mean I'm going to take a drink first, and then let's look at it. Questions? While you're thinking of them, because there's lag, I see we're already at 45 minutes. I'll soldier on. Ask the questions. They are all good. So, back in our Eagle control panel, which is that window that pops up, Palmer has a question. Can you publicly share the diagram for a DigiKey product? I'm not quite sure what your question is, Palmer. Tell me more. While you do, back in our Eagle control panel here, where we started our schematic and things, and actually I should save my board as well. And now that I have, you'll see that my schematic and board that I've made have showed up in my project here. And if I were to save more schematics and things to my project, they would all populate in the same place, which is really handy. I similarly have a place where it holds my libraries. So let's make a new library of parts that I can hold this switch design in, and maybe some other designs I might do in the future, maybe for the same project or others. So much like before, I'm going to go to the File menu, go to New, and do New Library, and it's going to pop up with a new library window. Let's see, Palmer's clarifies, when you make a custom layout for that switch, can you make it public for others who buy that switch? Not through DigiKey. Or through some of the other manufacturers. You could publish it on, say, your blog or on Twitter, but they don't have like a sort of a user-generated repository. You find a lot of them on GitHub for like semi-common parts. Like a bunch of the ham radio people have a standard-ish library of, say, like SMA connectors and BNC connectors. Oh, but you know who has a really useful library of common parts? And it's a little sidebar, is SparkFun and Adafruit. And I'll actually peek in those real quick here, because I've downloaded the SparkFun ones. If I open up my libraries folder here, and open up I think it's just in libraries, download, yeah. So I've downloaded like the SparkFun switches library, the SparkFun resistors library, some ICs. So like a lot of the parts that they sell, they have made Eagle parts for to make it easier to integrate them into your, or parts that they have used in their products as well, make it really easy to integrate them into your product. So check out, just Google SparkFun Eagle libraries or Adafruit Eagle libraries, and you'll find those. Some common parts in there, not all of them, but a good place to start. But now that we've made our new Untitled library, I want to introduce you to this screen. So which has devices, footprints, 3D packages, and symbols. We're not going to worry about 3D packages today. It's kind of out of scope. A device is an electrical thing you might add to your board. So when we use the add command, we're adding a device to our board. A device consists of two things: a symbol, which is the representation of your thing on the schematic, right, which is an illustration of sorts, and the footprint, which is how it shows up on your PCB. So that's the pads, any labeling, the through holes, all this stuff. That is the footprint. You can have a device with multiple footprints, the same way that when we added that Max 485 chip, there was a through hole version and a surface mount version. They could all share the same symbol and be different footprints if you wanted them to be. And then you would wrap them together into a single device, which represents a combination of a symbol for your schematic and your footprint on your PCB. So let's look how we make up all those things. Let's start with making our symbol. And I want to show you the data sheet for the switch that I'm going to use. It's this little adorable switch. It's so good. The JS202011 SCQN, which if I open its data sheet here and scroll down, is this guy. And this is how this switch in particular works. It's got 6 contacts here and 2 little sliding sections here. Either in this sort of starting position, pins 1 and 2 are connected, and 5 and 6 are connected. When I slide it over, pins 2 and 3 and pins 5 and 6 will be connected. Sort of 2 sliding bridges there. So this is just straight from the circuit diagram, from the data sheet. We're basically going to recreate this to drop into our schematic. So I'll start in my symbol here, and I'm just going to name this symbol after the part that I'm emulating. If this was more of a generic symbol like an LED, I might call it a more generic name, but just so I know what it is, I'm going to name it after the part. Say create new symbol. Yeah, don't mind if I do. It brings me into our symbol editor, which looks a lot like our schematic editor. A lot of the same tools, and a lot of them are just missing. So what we're going to need is these 6 points of connection for our switch. And we sort of talked about when we were looking at the schematic editor, those points of connections are called pins. So we'll use our pin tool down here to add those pins into our part. So let's add 1, 2, 3, 4, 5, and 6. And you can see I sort of haven't spaced them out super great. So again, I can use the move command to move those over where I need them to be. This text, unfortunately, is locked in its relationship to the pin position. You can't sort of move it around. So you end up sort of positioning things so that text is readable. So we've placed our 6 pins here, and it would be great if they could be numbered in the same way that they are in the datasheet here. So much like on a schematic, we can use our name command, which again is this R2 command, or type in name. I'm going to name those pins so they match our datasheet here. So I'm going to name this pin 1, I'm going to name this pin 2, name this pin 3, and so on. That's pin 4, right? Yeah, Name this pin 5, and I'll name this pin 6. And now, because this isn't a particularly evocative diagram of what a pin looks like, I'm going to use the line tool again to draw a symbol that sort of looks like a schematic symbol for this switch. We'll draw a nice little box. And then, so I remember how this works, let's see, I'll draw a little box here, and then I'll draw my arrow, much like on that circuit diagram. Maybe I'll change the drawing mode here, and we'll draw a little arrow so that the box goes that way, something like that. So let's say this is my sort of quick and dirty symbol for this switch. And you could take as much time as you want to draw your symbols to look really nice. You could also name these things not just by numbers, but if this was a part that had a power pin, you could name the pins VCC and ground and D1 and D2 and various things and give them nice evocative communicative names. But for the sake of tonight, we'll add some pins and we'll label them, and we'll draw a nice little switch diagram here. I'm going to save that real quick. It's going to ask me to save my whole library. I'm going to call this, Stream 614 as a library to work with. And we'll see it's added that symbol to my library of parts here. So now we have a symbol to put on the schematic. Let's make a footprint to go on the PCB to go with it. So I'll come down here to the add footprint command, or I could come up to the footprint icon in our menu here. I'll say add footprint. And again, I like to name my footprints after the parts that I'm making. If it was a more generic footprint, you could name it sort of whatever you want. So I'll say add a footprint, create new footprint, yes, and it brings me into this screen, which looks a lot like our board layout screen, again with some of the tools taken away. I have move, I have copy, I have rotate, I have name, I have text I could add, I have line, but really what I'm going to use is these two a lot, which are pad, which makes an SMD pad that only exists on one side of my board, and the through hole pad, which makes a pad with a hole in it that goes through all the layers of my board. So I'm going to use those to create the footprint, the space that my part takes up on my circuit board. So once again, going back to the data sheet for my switch, let's scroll up here, and any good data sheet, really any data sheet that you shouldn't throw in the trash, will have a diagram like this one showing you the PCB mount dimensions for your part. And so our job will be to translate these into our circuit diagram. So let's see, so our pad dimensions, and it looks to me like these are in millimeters and not in mil, unfortunately. so they're spacing about 3 point something across here. That's almost certainly going to be millimeters and not mil. But not to worry, we can change our grid temporarily to work from mil to millimeters. So let's say I want, instead of a 1.27 millimeter grid, let's say I want a 1 millimeter primary grid and let's say a 0.5 millimeter alternative grid. And we see things resize themselves to match, so that those work out well. So now I'm working in a grid of millimeters, since our spacing is going to be in millimeters here rather than a mil-based grid. And that's fine. You can mix and match as much as you need to, depending on whether your parts are metric or imperial or so on. So our pad sizes are going to be 1.2 millimeters across. It tells us they should be here. And honestly, these diagrams and data sheets are often really crappy. So I can see I have 3 millimeter spacing between them and 8 millimeters across the whole thing. So it's going to be 2.5 millimeters tall. So I need a pad that's 1.2 millimeters by 2.5 millimeters. So if I come in here, I select my SMD tool, my SMD pad tool. If I come to the size field in the top here, I can just type in how big it should be. So I'm going to say 1.2 millimeters by 2.5 millimeters. And I like to put the units right in there, just so I know it's going to be millimeters and not mil. I'll make sure we got everything right. So I hit enter, and now it's given me this 1.2 by 2.5 millimeter pad to place. So let's figure out where the center of it goes. Well, let's say the center two of these will go on center line. That'll make our lives a little easier. Where is the center of this pad? Well, it's half of 3, so 1.5 millimeters up, and then half of 2.5, so 1.25 millimeters up. So was that 2.75 millimeters up? So let's change our alternate grid to give us quarter millimeters. If I go 2.75 millimeters, that's where our pad will be. And then spacing between them is 2.5 millimeters in either direction, right? So we can sort of assume that there's 2.5 millimeters this way and 2.5 millimeters this way. So if I go here, I'll tell you, I'll just copy that pad. We'll go 1, 2, 2.5. We'll copy this way. Well, let's see, 1, 2, 2.5 millimeters that way. And then I'll use my group command. I'll drag a box, so I'll group all of them together. Now that I have them grouped, and this is, I alluded to earlier, copy paste works a little bit differently. If I use my copy command over here, copy, and then paste, now I get a paste box on my cursor here. And we'll want to go again from center line here. If we go from center line, I want to go, let's see, 1, 2, 3, 1 millimeter, 1, 2, 3, 2 millimeters, 1, 2, 3, 2.5 millimeters down. So that's going to be the layout of the surface mount pads for our parts. And if you're having trouble visualizing this just from the editor, and I know I'm slamming through stuff here because, well, it's been, about 40 minutes already. Let's see. So that's ultimately going to become this part here. So here's our 6 little pads that we've just drawn in our schematic editor. So you can see as I hold them up to each other, that's the 6 pads that we've sketched out there. That'll turn into that part on our board, which ultimately, as I grab the completed one, from here, that's going to be where this little switch will ultimately end up soldered. Palmer asks a good quick question. What is pitch for electrical components? Pitch is typically the spacing between pins. So for a bit of a header connection like this, or like we have on our Arduinos, there are 0.1 inch or 100 mil between pin connections. So that's 100 mil pin pitch. With a Phoenix connection, like Chris is mentioning, if you have, let's see, I think I have some terminal blocks here. Yeah. So if you have, the distance between adjacent slots in this terminal block here would be the pitch of those blocks. So I think this is a 200 mil pin pitch terminal block. So that's connections between adjacent pins. When you see pitch in relation to either header connections or surface mount parts. So like for example, here's a little tiny surface mount part here. I think those pins are 0.8 millimeter pitch. That refers to the distance from center line to center line. Good question. Or edge to edge. It's not spacing between, it's spacing along. So center line to center line of each of the adjacent pins in that part. I think these are 0.8 millimeter. It's TQFP, which varies, so I'm not 100% sure. But that, yeah, it refers to spacing between adjacent pins. And it's good to remember when you're thinking about with hand soldering some of these parts, like, looking at this part and it was like, oh, it's a 0.8 millimeter pin pitch. Can you solder that by hand? It's like, oh, I think so. And it turns out yes, but it was a little touch and go. So thing to remember. Yeah. So center line to center line of adjacent connections. Coming back real quick to our switch module here. This is the footprint in terms of the electrical connections, but it doesn't honestly tell us a whole lot about the part itself, nor does it really. It's nice for the footprint to tell you not only like what the part is connected to, but like something about its physical layout. So we see on this circuit board, like I designed it so that these two FETs could lay down in that slot, or put a big fat transformer here, or put a small transformer there. And that helps with hand assembly and placement and illustration. It's just good practice. So let's add some of that information onto our new symbol here. So going back to our data sheet for our part here, and you can see so much of this is just like read the data sheet and get it into the program. We can see that the actual dimensions of the switch body are 9 millimeters by 3.6 millimeters here. What I want is to create some labeling on my circuit board that sort of conveys the size of this part. So I'm going to use the line tool to draw that on to the T-place layer in my layers drop down here. So you can see there's a variety of things that start with T and P. Have T-place, B-place, T-names, B-names, T-name values, B values, and so on. That refers to your top solder mask and your bottom, your top silk screen and your bottom silk screen. So anything I draw on my T-place layer will be the silk screen on the top of my circuit board, which in this case is where I want it because my pads are on the top. But I could also put some labeling, if I had a part that was sticking through my circuit board, I could make a part that has labels on the top and the bottom, and they might be different depending on what you might be accessing from the top or bottom. So I'm going to draw some lines onto my T-place layer. I'm going to select my right angle tool here because I think that'll be useful for me. And what did I say? I said 9 millimeters by 3.6. So let us count over here. We'll go 1, 2, 3, 4, 4.5. So this is going to be this edge of the component, and then I'll go up 1 point. Let's go up just a full 2 millimeters here. We'll give ourselves a little wiggle room. So we'll go up, we'll go over here, and now we go over 1, 2, 3, 4, 4.5 millimeters this way and down. And that's going to be the outline of the top part of our board. And now we'll just repeat that on the bottom. So we'll go here. I'm going to make use of that right angleness of there to make that drawing a little bit easier. So that's going to be the outline, the T-place layer of my board. It's okay for it to overlap the copper pads here. The manufacturer won't print silkscreen on top of exposed pads by default. So you can draw right over it and it won't be a problem. And then just so it's like extra communicative, I'm going to do a little replication of the symbol here, just drawing some more lines just so like I have a nice representation of like, hey, this is a switch, solder it in place here, you dummy. That's what you meant to do, right? So this will be my footprint for my device. It's going to represent my pads and my silk screen that are going to end up on my device here. You'll notice I don't have to specify for myself like where the solder mask should go. I just need to specify the copper pads and connectors, and the manufacturer takes care of like, all right, solder mask goes everywhere except on top of pads by default. Totally good, right? So we'll save that. We'll come back to our library manager. Come back to our table of contents, and we'll see we now have a footprint and a symbol. So now we need to create a device that links the two of them together. So I'll click this add device command, and again, I'm just going to name it after my part, JS 2020-11. Okay. Create new device. Yes, I will, please. And it brings me into my device manager here. Which I think the interface here is just a little bit confusing, but once you get it under your belt, it's totally easy. We're going to use the add part command over here like we have before to add in a schematic symbol. And you'll see by default, it only brings in parts you have locally, so I'm going to choose the only symbol I have and drop it down into what feels like the symbol editor here. And you can see it's brought in my various pins here that I drew in earlier and their various names. And then I'm going to need to associate a footprint with it using this new footprint button over here. It's going to ask if I want to do local package or add from web. I want a local package, something on my computer. And we'll see again, I only have the one package I've made so far, the JS 2020-11 package here. So we'll hit OK. So now we've brought those two things in, but there's one more important step, and that is to tell the device which of the physical pads on the footprint correspond to which of the pins on the symbol. Because you can imagine on this symbol, if things were not laid out in the same way physically as they are on our footprint here, we might have to do a process like, oh, well, the VCC pin's up here and ground is over here and so on. And in fact, to make that easier, I'm going to go back to our footprint editor for a second, and I'm going to name my pads here the same as they are on the switch. So again, I'm going to use my name command, and that'll be pad 1, pad 2, pad 3. Up here, we've got pad 4, pad 5, and pad 6. Right? So that's the same as our in the data sheet here. That's the same names they have. That's the same as we use for our symbol. And that's going to make it really easy when I go back to my JS2020 device to connect them. Pin says, do you have to link the pads to the pins of the schematic? Yeah, it's exactly what we're going to do here. So you might have asked that a while ago, and I apologize. So what I'm going to do now that I have my footprint added here, and I have my symbol added here, I'm going to use this connect button. And that's going to bring up a list of pins in my schematic and a list of pads on my footprint and ask me to select which ones should be connected. Now, in this case, because they're numbered in the same way, that makes my life really easy. I'm going to connect 1 to 1, 2 to 2, and so on, right? So now pin 1 is pad 1, pin 2 is pad 2, and so on. 1, 2, 3, 4, 5, 6. You can also connect multiple pads to a single pin, say if you had multiple ground pads on a device or multiple power pads on a device, but mostly you're going to be identifying one pin with one pad on your device. So once we have done that, oops, and now I need to save my changes and my window size is making things a little screwy, hit OK, and now we are good to go. There's other things you can do in here. You can add a description to your part, which I encourage. You can add attributes and things, but for the time being, this is the critical parts. You make a symbol with some pins, you make a footprint with some pads, you create a device which connects the two of them together, and you use the connect tool to tell it which pads are which pins. Cool? So now that we have created that device inside of our library, we're almost ready to use it in our PCB. One small thing we need to do is actually activate that library for use. So back on our control pad here, if we come back to the libraries section, come down to libraries, which is libraries that you've made or libraries that you've installed yourself, we'll see our Stream 614 library that I saved this as earlier. It has a little gray dot here. I'll want to click that so it becomes green, and that means that library is now active and is going to be ready for use. You can choose to enable or hide libraries from yourself just to keep that list a little more manageable. You can see I installed all the SparkFun libraries and then only activated the one for microcontrollers and left everything off because I'm not using them right now. And I have some other libraries that I've made for various things. It's like just to keep them separate. Like I don't need to enable my my Pogo pins library. I don't need that for now. I'll turn that off and so on. If I was being really thorough, I could go through and like turn off a lot of the other stock libraries, but I'm lazy. But now that we've enabled our Stream 614 library that we saved earlier, I can go finally back to our schematic editor and add that switch into our device like it was any other. So using our add command, I will find our Stream 614 library that we've made, and open that up, and now here we have our switch, JS202011, and that shows up in our schematic like it was any other part. Ta-da! So, of course, I'm going to have to do a little work to integrate that in. I'm going to need to group and move some things over, then move this switch into place. So, again, selecting things with the group command, then with the move command, control right-clicking on any of the parts to move those over. I'm going to move this switch in down here. And what I think I will do, so let's see, how do I want this to work? I think what I will do is try and preserve a little bit of the this naming that we did earlier, but not try and do everything just by names, because I think that will get a little bit confusing. So we'll take just a second here. We'll move that over. We'll move this over. And then, so I'm going to delete these nets so that we sort of get rid of their labeling, and we'll come back in with the labeling later. I'm going to use the net command. So let's see, I need the receive. Let's see, we'll connect to the center pin here, and transmit will connect to the center pin here, and we'll say that this direction, when the switch is over here, we want things to be connected, and when the switch is down here, we want things to be disconnected. So when the switch is up here, this is the receive side, so this net, where it's connected to, this wants to be my RX net, And this side, this wants to be my transmit net. So that's how that's, and then we'll leave these two disconnected, which is fine. Like, we don't need to connect those to anything. Oh, and then I didn't actually need to delete this net here. That control net is going to work in exactly the same way as before. We'll name that dir like we had before and reestablish that connection. Right, so that's our switch now integrated into our schematics. And it feels like I'm flying just a little bit here. I do apologize. I know we're deep into the night. I would love to get this thing laid out and assemble or manufactured for us this evening so we can put the button on things. So it's not our longest episode overall yet, but we're closing in on that. So we'll move at a good clip. Feel free to ask questions, of course. I don't want to leave anybody behind, but this is a long one. It's a lot of good stuff to know. But hopefully not too intimidating. Like, all this, it takes some getting used to the interface, but like making a PCB these days is really not that hard, and that's awesome. So now that we've added our new switch part to our circuit board, we can see that because we deleted some of those connections and re-added them, it's ripped up some of the copper for us. So for example, this dir pad needs to be reconnected here. It's broken the connection between our RX trace and this pin, which used to be the RX, was directly connected, but it hasn't ripped up the rest of that. So we might need to do a little bit of cleanup there. So I'm going to use the rip up tool, and actually rip up has a fair number of options. I can do rip up just a little section, rip up connected copper or connected copper on same layer is really useful. If I use that option, I can rip up basically this entire trace back to where it started. And similarly, I can rip up that entire trace just because I want them to go away and start fresh. We'll move our switch into place somewhere up here, nearby transmit and receive. And just judging by our air wires, I think that is going to do us just fine without too much overlap. And now we'll complete the process of routing that switch in. Let's see, a couple quick questions. Palmer says, you do a full schematic on paper, then redraw it in software, or do you start in software? Depends how complicated the design is, to be honest. Mostly I will have a good enough sense of the design to start sketching it out in the software, in the schematic capture part. But I will typically go through like 2 or 3 revisions in the schematic editor before I bother to start laying it out on the board, if that makes sense. It's not uncommon to like think about general layout on paper and be like, this is Arduino and this part, and do I need a power regulator here, and what kind of connectors I'm going to have. Thinking about connectors early is really helpful, because often if you're thinking about how connectivity, those are going to be the parts that drive like the size of your board. So thinking about things like, barrel connectors or various switches or what have you, is not a bad place to start thinking about circuit board procedure. Let's do a real quick route of all this stuff. I want to show you how to deal with those ground connections, and we'll get this thing manufactured. So once again, I'm going to use the route command to get some of these traces routed in here. We'll bring this RX command around the back. Routing is kind of as much an art as it is a science. You get used to seeing sort of configurations and knowing how to deal with them. And it's nice to keep things nice and pretty. Like, I want this trace to go right up between these 2 pads and terminate nicely in there. So this, again, I'm going to make use of the ability to route traces in between pads of my own components. A really handy trick. I might move this a little further away. I might not bother. So that looks like all my traces except my ground traces routed. Yeah? Looks like it. I could do a DRC to double check. But let's take care of those ground connections. So it is common to, on a PCB, to make use of not a trace that is a ground, not a single wire, but a whole flooded area of your board called a ground pour. That gives you a really low impedance, a little low resistance way of like holding a wide connection area for a ground connection. Because you don't want you want ground to be ground, right? Ground is ground everywhere. And to accomplish that, right, to really think of like ground is 0 volts is everywhere, it's the same thing. You want a nice wide connection area. So it's common practice to sort of flood unused areas. You can see on the back of this circuit board, this entire area is ground, with the exception of that little trace staying through, and that little trace, and that little trace. But everything else back here is ground, and a good area on the top side as well is just ground. So we're going to look at how you do a ground fill to sort of fill lots of areas with ground. And like I said earlier, if you were doing a 4-layer board, it would be common to have like a layer that's entirely ground, a layer that's entirely power, and a couple of layers to route signals through. On a 2-layer board, we often have a ground layer and then route our power sort of more manually. Just for layer limits. But here's how you create a flooded area that is a ground layer. We're going to make use of, in the board editor here, this polygon tool, which looks like a pentagon. Click on that. And I'm going to set its width, its line width, just down to 0. And then I'm essentially going to trace the outline of my circuit board here. It's okay if this one is not terribly precise. But I want to make sure this lines up right. So I'm going to make use of my grid just to make sure that the ends of my polygon line up where I want to. And when it's complete, it's going to ask me for the signal name that's associated to this polygon. In this case, I'm going to choose that GND signal, which I know lines up with the signal name for my ground symbol. If I was ever unsure of what that signal was called, I could use the name command and click on the net in the schematic editor and say, oh, that's a ground net. That's what ground is called here. Similarly, we could click on any of the other nets and say, oh, that's our RX net. That's my N3 net. We didn't give that one a special name, and so on. Now that I've made that whole area my ground net, you'll see I had this dotted line representing that polygon. The next time I run a rat's nest command, it's going to fill as much as possible within that polygon with copper connected to that net, right? So we can see that things like these pads of the switch are not grounded, so it's spaced things out a little bit here, so things are not connected. But things that should be connected to ground are. We can see, the parameters here are a little bit off. You can see this very thin line here connecting this copper here to this ground pad. That's partly actually because I set that width down to 0. If I click back on the edge of that polygon, I adjust that width, say up to 10 mil, and come back, we can see we've connected from our copper into our ground pad here. So now this pad, which I didn't route earlier, is connected to ground because this entire area is filled with copper connected to ground. Same with this pin, that's the ground pin on the Max 485. Same with our ground pin on the Arduino up here, and so on. The reason that these are connected only by these sort of cross hatches as opposed to all the way around is because if this was connected by copper all the way around and we went to solder to it, we'd have a whole heck of a lot of copper to try and heat up to solder to this pad. This is what's called thermal reliefing. It's a way of making really solid connection between the copper layer and this pad while also not having so much thermal conductivity that we'd have to heat the whole board up just to solder to that. So that's why you get this crosshatch and not just a solid connection. But now we should have taken care of most of our ground connections, except, of course, there's a couple that are not. So I can see I didn't route my direction pins here correctly. I've still got an air wire hanging out, and I have this this fill currently taking up the space in between there. That's fine. I can use my route command and just route between them, and then next time I run a rat's nest command, it will pull back that fill for me. Similarly here, I've got this net. Somehow I've deleted my net that was going up to my transmit pin here. And again, it looks like these things are merged together, but then next time I run a rat's nest command, again, it pulls that fill back for me, which is really, really handy. You can see it would be possible, like with enough traces, to cut off areas of this ground pour. So just a thing to watch out for if you need that area to be grounded. So now I have a ground pour on the top layer. I'm going to create a ground pour on the bottom layer too, just for thoroughness. So I'm going to select bottom layer. I'll select a polygon. And again, using my grid to make sure things line up nicely. I'll connect that to signal GND. And the next time I rat's nest, you can see now we have both a red and a blue ground fill. Now, if you ever... traces are 6 instead of 12. Oh, did I shrink that trace size? That's all right. I'm not going to worry too much about it because I want to press on a little bit here. But good catch, Chris. I should check my trace widths there. If looking at if these fills is ever getting in the way, like now we have this bottom fill kind of preventing us seeing what's going on, there's a couple things you can do. You can come up to the layer settings up here, which looks like a stack of playing cards. And this lets you toggle the visibility of various layers on and off. We got top, we've got bottom, we've got pads. We can turn off our air wires, our unrouted wires, our T-place, and mention so on. You can play with turning on and off layers here. You can also, let's say we wanted to see the, let's see, also I'll turn off that bottom layer. There's not much to see there. But let's say I wanted to, not look at my fill in my top layer here, but I still want to see the top layer traces. I can use the rip up command on the edge of my fill. You can see I click on that dotted line that I originally drew out here. If I double click that on my top layer, rip up, and make sure that I'm in trace polygon or via mode up here. There it is. I double click on that. It temporarily removes the fill, but still lets me see that layer. When I run a rat's nest, it will come back, and when I use the rip up again, it will temporarily be hidden. So a little weird double overloading of the rip up command there, but that just is what it is. So we've looked at routing, we've looked at polygons, we've looked at rip up. We're not going to look at the auto router tonight. That's going to be, I'm going to leave that as an exercise to the class. What Chris is mentioning is a tool that basically will route your traces for you. It hides somewhere in here. Where is our auto router? Auto router is this little symbol with a lightning bolt here. You can say like which preferred direction do you want to route, how much effort do I want to put in, and so on, and we'll try and route your traces for you. The auto routers are not, they do fine. They will make the connections. They often leave you with kind of a mess of a board, especially with lots and lots of parts. So it's good practice to route your boards yourself, or to route the critical parts of your board yourself. Like I have definitely laid out boards where, you know, I would need to route like the incoming signals and power and ground and create a ground fill. And then, you know, I have 16 inputs and 16 outputs and I just need them to get connected. I might let the auto router do its thing, and it comes out a little messy, but fine, and things will end up connected, and so we'll sort of live with that. So auto router, an option for more complicated setups, especially if you're doing like lots and lots of pins, mostly going in similar directions. It'll do a pretty decent job, but like I say, you can explore that on your own time. I'm going to run one last DRC, and then we will export this and get it ordered. So I'll run a design rule check, I'll hit check, and I'll see it didn't even pop up a window that says DRC no errors. Well, that's great. That's really quite good. I'm sure there are like, you know, emotional and ethical errors on this board, but there's no design rule errors from the rules that we've defined for it, which is awesome. So give that a quick save. So let's look at getting this board. Let me take a drink, and then we'll get this board manufactured, and we'll get you all out of here to bed, putting on pants, taking off pants, you know, wherever you're at in your evening. All right. Palmer says, where do you edit the silkscreen? Okay, good question. So you can see the silkscreen has come from a few places. We can see that the parts that had labels attached to them, this has come with them. This part that we made, because we put information on that T-place layer, that silkscreen has come along with that part and has put itself on the T-place layer of our board. For part labels like this JP2, JP3, you know, IC1 that have come along with, we get this little plus target that we can use with the move command. We could move those labels around so they lined up more nicely, maybe weren't overlapping traces, maybe we're all in the same orientation. We can see like our jumper here has gotten a weird label on it. We can move our values around. Whether you need values or not on your circuit board is like up to you. Like if R1 and R2 are always going to be the same, and if I can't quite squeeze in what that value is, I might choose to delete it. Like I use the delete tool and just get rid of that value there. Leaving reference designators, which is the technical term for like R1, R2, IC1, leaving those reference designators is really a good idea. The values are more flexible. Things like part names, like if you can squeeze it in, great. If not, might as well just blow it away. If you want to draw your own values on the silkscreen, you certainly can. You can use the line tool, and you could say maybe on the T names layer, you could draw a line. You could draw a circle, you can draw an arc, and sort of draw with the line and various other illustration tools. You could draw various arcs and circles and give yourselves things to target. You can also use the text tool and say things like, "Hi, Palmer," create some text, and you can rotate that with the right mouse button, much like with the move command, and you can move that into place. Now, a thing to watch out for with the text that I would recommend is come in here when you select your text, using the info tool, which we have not looked at much tonight, using this info tool. Selecting that text lets you select, more specifics of position, angle, size, and so on. I highly recommend coming down to font and choosing vector. And that will, in general, I've lost it. It's gone. It's gone forever. That will change the font to appear somewhat more like this. That font will be the most compatible with the most board manufacturers, just to make sure that your text looks correct. So those are your tools for manually editing the silkscreen, line, text, rectangle, polygon, etc. A lot of the time your silkscreen has come along because you've added parts that have silkscreen attached to them. So if I was going to be, let's take an example, things like all of these outlines of the FETs and the transformers and things have come along from the parts that I added, but things like, I added a couple of 4-pin headers and I wrote low pass filter on there. I would really recommend, I definitely didn't do it on that board, things that are good to add, things like version numbers. And the name of your board. Like if you have, this is now, I think, version 8 of this particular circuit board, or I think version 0.8 of that I've been numbering them. If you're going to have a lot of boards that are going to be similar revisions, good to have revision numbers. Good to have like your name, fun to have the date so you can look back and remember like, oh, that was a board from 2003. Like that's kind of cool. So name, date, registration. If you think you might put a picture of it online somewhere, I like to put my name on them and like my website in case I'm like, oh, that's free publicity for me. But version numbers, if you could add anything else, that would be a valuable thing to add. I'm going to leave Hi Palmer on there just because I can. Other questions about PCB layout real quick? While I'll think of them, throw them in the chat. I do want to answer them. I want to show you how to get them ordered because it's really easy. I'm going to show you 2 different places you can order them. It's like 10 years ago, this would not have been possible. Now it's really stupid easy. So now I'll show you the really easy way is to order from Osh Park. So I've made this design in Eagle. I'm going to hit save just to make sure it's nice and saved. If I go onto the interwebs and go to oshpark.com.org, it's .com. Yeah, well, purple PCBs. They have a whole purple theme going. What's cool about Osh Park is you can directly upload your Eagle board file to the website, and it will make your board for you. So I'm going to go into my documents, go into my Eagle project. In my project called Stream, I have this board file here. If I drag and drop that into the website, one of the supported file types, that was a supported file type. Oh, maybe it's my project file? Let's just see if I browse for files. This will be I literally demoed this just yesterday, but I didn't try the drag and drop, so maybe I'm not doing this right. Email. Oh, is it because I'm... Oh, no, there we go. So we'll see. I do some processing here. And, oh, I was trying to upload the schematic, which, of course, it doesn't like. We'll go back there. I want the board file. Oops. Go to OSH Park. Let's try this one more time. Drag the board file into the website. It'll upload. It'll process. And when it does some thinking, and we'll see it comes up with a pre-visualized. So what it has loaded, essentially, if I drag this in here so we can see it, this is what the actual file looks like. It's basically a text file with lists of geometry and traces and pads and things that Eagle is using to store that data. OSH Park has ingested that data and used it to create a preview of our circuit board, which is great. So you can see it's got this is what our circuit board will look like when it's fully manufactured. It's got our silkscreen, it's got our labels, it's got Hi Palmer in there that we just put in, it's got our header pins there, got a preview of the bottom, and say, I can enter a board name, I can call this the stream demo, it's a good board, I'll enter my description, and email address, I'll put in my email address. I don't care, well, I guess I don't really care if you see it on the internet because it's not that secret, and hit continue. Let's see. Palmer asks, what software generates Gerber files? Palmer, I'll get to Gerbers in just a second here. Oh, I'm going to log into my Eagle account, which I apparently made. Oh, it's going to make me re-upload. Well, that's just fine and dandy. How many crawlers have I had, Chris? I'm about to kill this one. I finished my glass, my adorable wedding glass, and now I'll just kill this crawler. Like I say, if it feels like I'm slamming through this, I feel like I'm going 1,000 miles a second. It's really just because I'm aware of time. Like, it cut awfully late, and I don't want to. I appreciate all of you, and I think this is a really cool time, and I have done a less good job than usual of keeping to 90 minutes, as Nate would say. All right, so I enter a board name and description. This is a good board. It's also told me that it's found that it's a 2-layer board of a certain dimensionality. I can hit continue. And it's going to ask me to verify my design. It says board top. This is how your board will look when you get it. And if we compare that to this board, which looks, slightly different because we did the routing new and, placement's a little bit different, but you can see it pretty well matches up with, with that design that it's previewing on the website here. Board bottom will look like this, and then it's going to preview some various other things. Say, here's all the holes that we're going to drill in the board. Here's the bottom layer of copper, if we were looking at it raw. The board outline, right? Here's what we think the outline should look like. So again, this is just a rectangle for us, but if we were doing something, more nuanced, we'd want to verify that the outline was ingested properly. Here's our bottom solder mask. So this is the exposed copper that we think we'll have. Bottom silk screen, top layer copper, top solder mask. It's just a way of verifying that everything that we think should be true from how we designed it in our design software has been ingested properly by OSH Park, sort of taking in that data, generating all these layers, and sort of seeing what it thinks you should look like. This is a really good time to take some time and go through and say, okay, is this what the labeling should actually look like? Like checking the labeling and the fonts and the silk screen. Are all my drill hits here? Is my copper looking cromulent? This is a good chance to just verify that everything looks all right. I'll hit, if everything looks good, I can hit order, and it'll let me sort of go through my order options. When you're ordering from OSH Park, orders are in quantities of 3, so you can order 3 or 6 or 9 and so on. 3, they're ordered by cost by square inch. So 3 PCBs at an inch and a half, $20, totally easy. I have some options here. I could go to 2-ounce copper. So there's a medium run option if you're doing lots of boards. Let's say I think it's 100 boards. I don't know what qualifies you for medium run. Super swift services like fast turnaround, fast shipping. Flex PCB if you're ordering flexible circuit boards, which we won't get into tonight. Black substrate clear mask is a really classy option. It's a little bit expensive. And it looks like, oh, this is my Q-Lite test board order. I still have an OSH Park. That's pretty funny. Let's delete that. Once this is all looked right and I have my order, oh, this is good. So those 3 boards are $7.15 each. That seems like a much more reasonable price. So about $2 a board, quantity 3. If I order, say, 12 of them, ask that update, $28 for 12 boards. And then I could go to checkout. Now, I'm not going to put in my credit card details on stream because that seems like an especially bad idea. But I could put in my shipping address and then have these shipped to me, and they would show up in a week and a half. And that's all there is to it. Literally, you drag and drop your Eagle file in, you double check that everything looks good, you tell it how many boards you want, and they will ship them to you. And if something goes wrong, they will email you and say, hey, this doesn't look, something is strange, something's not processing here, check your file and try again. Super great service. OSH Park is awesome. The other service I will share with you, so I encourage you, OSH Park is an American manufacturer. They do great work, and they really have pioneered hobbyist level PCB manufacturing. I do also want to show you the flip side of things, which is a giant based in Shenzhen PCB board house manufacturer, like JLC PCB, who I've also ordered from. Show you what that process looks like. And this goes to what Palmer was mentioning in the chat a moment ago about Gerber files. So, Eagle PCB software has their own file format for how they save your schematic and your board and things. How they, save that internally, save it to your hard drive, bring it back at the, when you work on it the next time. There is an separate industry standard file type for defining details of circuit boards called Gerbers. So when you're in your Eagle PCB file here, either on the board menu or the schematic menu, because it's all in the same project, if you go into the file menu and do generate cam data, or you can click on this little factory with the download arrow in the top center here. If you click on that, it will tell you it's going to generate these various Gerber files. We can see they roughly correspond to the layers of our PCB. We have copper top, copper bottom, solder mask top, solder mask bottom. Solder paste top and bottom would be if this was getting assembled robotically, silkscreen top and bottom, and so on. The defaults here are generally pretty good. If you ever wanted to mess around with like what it's actually generating, you can go into the cam processor, which is this other factory icon. Oh gosh, we're not going to be able to see that. There we go. And you can tell it exactly, when you're thinking about the top copper layer, which of the Eagle layers corresponds to solder mask top, solder mask bottom, etc. For example, like if you wanted, right, here's a one that has gotten me a couple times. By default, the top silkscreen layer inherits from the top placement layer and the top names layer, but not the top values layer. Like let's say I wanted to say like 1.5K or 2K or what there. I could say edit layers. I could add my T values layer to that. And that would make sure that my values show up on my silk screen over here, which I definitely want them to. So that's my, I've edited those layers so they show up appropriately. So now that I've got that cam processor all laid out, and I can save changes to my cam job, I'll save that as my cam file. And the next time I do generate cam data, it's going to generate all these Gerber files. I'm going to generate them. It's going to give them me a name and a date. I usually put a time on there as well because I'm generating a bunch of these typically in series. And it will pop open a folder with where I'm storing my project, and it'll show me, if I can zoom it out, it's put those all in a nice zip file for me. So that contains all of, in this Gerber format, this industry standard format, the information for my top copper, my bottom copper, my solder mask, my silk screen, all that, all nicely zipped up and ready to use. And we can make use of those Gerber files from my CAM processor to get this board made from somewhere like JLC PCB. I think this will be kinder to me if I do a quick login here. Yeah, that works pretty well. So there's lots of different board houses. JLC is one I've used. I'll show you how to find others in a second here. I'll just go to give me a quote for a circuit board, and the first thing it's going to ask me here is to add my Gerber files. You can see only zip or RAR, which is another compressed file type here. Only zip or RAR accepted. So I'm gonna say add my Gerber file. It's handily in the right place already. I'm gonna select that zip file that my software just made. It's gonna upload it, and similarly to OshPark, it's going to process that data and generate a preview for me so I can do a little bit of checking that my data has been ingested successfully. So we're processing, and again, so here's what it thinks my circuit board will look like. You can do sort of the external Gerber viewer if you want to. This does, has a nice preview. And it tells you a little bit about like how small your drills are, how far your traces are, and various things if you wanted to look at them. But mostly you're just verifying that like the circuit board that you designed in software looks the same as what the website has ingested. So the website gives you a few more, JLC PCB gives you a few more customizability options than OshPark did. So I want to. There's some good videos online talking about this, but I will blast through them real quick because it's almost 10 o'clock. We're going into extra innings on this one, folks. But I swear we're at the home stretch to continue the baseball metaphor. Let's talk just a little bit about PCB ordering options. The number of layers and the dimensions are something that it's going to have automatically figured out when you uploaded your files. You don't need to set those. How many PCBs do you want? The default is 5. You could order up to 25,000. It'd be a little expensive. $1,000? That's what, 20 cents a PCB? That's actually not awful. I'm not going to order that many. But it also says, we recommend you prototype before small batch PCB production. So let's set ourselves back down to 5. That seems more reasonable. How many different designs are in your files? You can upload multiple files at once and sort of combine them into the same order. But in our case, we just have a single design. Delivery format. So if you're sending your PCBs out to be assembled, that is having parts put on them, they can't be, individual, like no one, this is not going to be a thing that a machine is going to be able to hold and put parts on. You need to be in a larger form factor called a panel, which there's some industry standard sizes like an A4 piece of paper, maybe 8 inches by 12 inches, and some larger ones as well. So you'd want to say, hey, make my circuit boards, and either I've already arranged them in my software into a panel shape in this panel by customer, or you can say, hey, JLC PCB, please put these into a panel for me, and they'll add some padding that you can break off around the outside that gets you to that size limit, so that a pick and place machine that's going to be assembling your parts for you can handle this instead of working with a tiny little tic tac box size thing, handles a nice large sheet of these things and asks you to specify your dimensions here. But we'll just be ordering single PCBs that they will cut out of those panels for you and ship to you sort of loose in a box. PCB thickness, so again, 1.6 millimeters is the default, but you can order a variety of other sizes. You might notice over on the side here, they will, although it looks like you can go smaller. For some special ones, you start getting charged more. But if you have default 1.6, you don't get charged any more than the default price. Palmer, this goes back to earlier when we talked about color. If I select green as sort of the default, it gives me a little smiley face here. Fastest turnaround for 24 hours, recommended. How nice. But you can also choose, red or yellow or blue, and it will start charging you a little bit more as well. Here's where we get down into those surface finishes on copper that we talked about way back at the beginning. So we have hot air solder layer, where we have that very thin silvery layer of solder that goes across those copper pads. We could also do a lead-free solder layer, or ENIG, which is our gold plating. And again, those get a little bit more expensive. ROHS is a European certification that means basically lead and chemical free. So when you see ROHS, that's like European compliant, basically. We can choose our copper weight, 1 ounce or 2 ounce. Gold fingers. So if you can see kind of a little picture here. May I zoom in? If you have a board edge connector, it's a common practice to do just those connectors in gold because it is such a good conductor. So you have an option to basically do just those connectors in gold and the rest in copper, so we're not spending too much money. It's only giving us an FR4 standard PCB material type. You can a flying probe test, which is basically a machine that moves probes around to touch various points on your circuit board and test whether they should or shouldn't be connected. The default is to test it. You might as well leave it. Castellated holes. Castellated holes are super cool. If you're indulge, thanks, Palmer. I do feel bad for keeping you all so late, but I can slow down just a little bit, I think. And I swear I'll breathe as I talk about castellated holes. So let's look at this. We'll bring it all the way back around to home. We'll look at this little wireless module that we'll look at someday in the future. If we look at these two pads over here, you see these 2 points where we can solder in, a bit of a header pin. You can see I've soldered some header pins over to this side already. But you'll notice that these pads have something interesting about them. They have this little notch, this little shark bite out of the outside. That's called a castellated hole. And the goal of that is that this module, so, you could prototype this by, soldering header pins into it and, say, plugging it into a breadboard. But those exterior castellated holes are meant that you could actually just plop this module down onto another circuit board and solder it directly in place, using those exterior holes as sort of a connection point. Like this was kind of like a surface mount IC in a circuit board format. So it's super cool. A lot of prototyping modules use these castellated hole formats, so you can either prototype with them and solder the headers onto them and plunk them into a circuit board, or solder the whole module to another circuit board for use. You sometimes see this too with GPS modules or various sub modules that are meant to integrate into other things, that they'll have holes but also castellated edges so you can solder them directly onto other circuit boards. That's kind of cool. Thanks, Palmer. I appreciate you. So we don't have any castellated holes on our design, so we'll hit no. Remove order number. I'll leave the order number printed. That just means that they're going to print somewhere on your circuit board. They're going to add, a little extra printing of their own that they use to track in the factory. You pay a little extra if you're not going to include this. They have to do some extra labeling exterior to that. But so I usually just leave it on. They're usually pretty discreet about it. Even on a little tiny circuit board like this, you just end up with a little serial number somewhere. Totally fine. So that's all of our basic options, and that's basically it. So once all of your selections are made, you can save this to your cart. You had a couple of different shipping options. You can either ship, via China Post, which is pretty slow, like 3 weeks, but is free or cheap, or through, I'll just hide my address there, through JLC PCB, or through DHL. And DHL ships pretty quick. For those who have used them before, it's a courier service. My typical expectation here in the Midwest of the United States is if I put in a PCB order before, I don't know, before 5 p.m., say, not that they're operating on my time zone, but before, mid-afternoon on, say, a Thursday, I will receive these parts via DHL the following Thursday. Any weekday order tends to be about a 1 week lead time for me. I typically get if I order on a weekend, I'll typically get them like the following Monday, which is really amazing. And they are almost always running a special where you can get, your first 5 or 10 PCBs for $4 or $5. You pay about $17 to $20 for shipping. So, for 10 PCBs for $25 for shipping. So each one is maybe $2, maybe $3 for, what is really a very, very useful piece of equipment. Yeah, Palmer, it's really true. Like, I can't believe how accessible PCB manufacturing is to us now. Like this, and done in hobby quantities. And this is really a good reason to support Osh Park, is that they really pioneered this idea of, before, 10 years ago, like a PCB house didn't want to work in 5 boards, 10 boards, a dozen boards. They wanted to make 100,000 boards. They want to make your product. And what Lane at Osh did was to go to a board house that was willing to work in very small quantities and say, hey, if I do the legwork and take these designs from hobbyists and assemble them into panels, will you make 3 panels at a time? That was their minimum orders, 3 panels. They're like, yeah, okay, we'll work with you on 3 panels. And so that's why you have to order in quantities of 3. Is each panel is identical, and he orders 3 panels at a time. That will be, a panel that is, one of my design and one of Tom's design and one of, Jamie's design and one of Erica's design and so on. And they fab them out. He cuts them apart. You can actually see the end result of the cut apart from these little, hanging tabs that are left on them. You can just snap off. They're sort of, have little holes in between your circuit board and the tab called mouse bites that you can come through with a flush cutter and just snip off when they get to you, and file down if the surface finish makes a huge difference. So they really did pioneer this idea, and the whole reason that like JLC and all PCB and all these places exist is because Osh pioneered it. So, and they really have amazing customer service. If price is a real concern for you, and I know like for a lot of us it is, and especially these days, of course, it often is, there's a really interesting website called PCB Shopper, which lets you take the really basic, the parameters of your board, like some dimensions, some layers. Let's say I want 10 of them, and give you like a real rough and dirty quote from a bunch of online board houses. So I have my little board here, 2 layers, 10, whatever their least expensive option is, which sides have silkscreen. So you can save on money with some of the places, having only silkscreen on one side, copper weight, drill, gold fingers, and various things. I do a quick get prices here. And we'll see. Now, people also, some of the board houses put ads on this site as well. That's how this site sustains itself. But you can see like JLC PCB, PCBWay, Elecro, Seed, All PCB, and so on. They give you various prices, and also will quote them to you with shipping. So like for this one, e-packet delivery from China in 73 days will be, $10.45, and it gives you also a unit price per board. So like, these boards end up being 49 cents each, these boards for 84 cents each, and so on. It's amazing how much cheaper the boards get, because so much of the labor of this is in setting up the first parameters of a board. So let's see. So the cheapest option here is 52 cents a board for quantity 10. Let's do quantity 100. And just check out what that price break is. So even now from like JLC, you do 100 boards, we get down to like 12 cents a board plus shipping. If we order 1,000 boards, at some point we'll get diminishing returns, but just for curiosity's sake, down to like 5 cents a board. So we could order, 1,000 of these shipped DHL to be at my door in my experience about a week for $100. So let's say I needed, 1,000 of these little tiny PCBs. Now they wouldn't have any parts on them, right? I have to deal with assembly, and that can get expensive too. But I could get, 1,000 of this board shipped to me in a week for $100, which is wild. So that's pretty cool. I want to close tonight, so this is now a good chance to shout in any more questions if you've got them, and I'd be happy to address them. But the final thing that I have to talk about is some, this is like taking a circuit, putting it into Schematic Capture software, laying out a board, routing it, and getting it ordered. I want to throw out a couple of pieces of my advice for those who have stuck with me for the last 3 hours and 8 minutes, you heroes. Some piece of advice for people who are designing circuit boards for prototypes, and this is just straight from my personal experience. Things that you might want to consider for your prototype PCBs that you wouldn't necessarily consider for a production or a general PCB. So here's some advice straight from me to you. Thinking about power on your board. Does your board need a power regulator? You need a voltage regulator on it to give you your 5 volts to drive your IC or somewhat? Or are you planning on putting power onto it from somewhere else? If your board is gonna have a voltage regulator on it, like let's say it's gonna be a battery power project, it's gotta have a voltage regulator on it. For a prototype, it can be really useful to add an additional place to inject power into it instead of using the voltage regulator. So for example, this is a little prototype board I've been working on that's ultimately going to get a little voltage regulator right here. But for testing purposes, I just want, I don't want to put a voltage regulator on it every time I'm testing. I'm just going to squirt 5 volts into it and see if it works. So I have these positions on this board where I can just inject power into the board for testing purposes. Not something you necessarily include on the finished board, right? Because if it's going to have a voltage regulator on it, I don't need those points. But for testing, a really handy thing. Similarly, is your board going to be the core of a device such that it can provide power to other parts of your board? Do you need power egress? Do you need additional, if you're going to put a voltage regulator on your board, maybe you can provide 5 volts and ground to other parts in your system. Something worth thinking about. Test points we didn't really talk about. Test point is usually just a little surface mount pad that you put on your board. Maybe I can find one real quick. To show you, that allow you to give you a place to, stick a multimeter, basically, or stick an oscilloscope. Yeah, so here in our test pad library, if I go into PTR1, there's all kinds of standard sizes for these things, but the very first one is, it's usually fine. If I bring that back over to our board here, I get this little surface mount pad. It's little adorable. It's just a little pad hanging off by its lonesome. So let's say I wanted to be able to measure whether I really had 5 volts present on my power rail or not. I could attach a test point somewhere to my 5 volt line and route it into my PCB. And now that just gives me a real easy point to stick a multimeter probe on and test if I've got the voltage that I need. I could do a ground test point. I could give myself signal test points, right? If I wanted to be able to check whether these DMX signals were passing through here successfully. So thinking about adding test points to your devices from the test point library is a useful thing. Palmer asks, is test points what they talk about when they talk about bed of nails testing? So bed of nails testing, not exactly. Bed of nails testing is typically where you would have either a test jig or a mock circuit board, but instead of having components on it, it would have an array of sort of hard pins, often spring-loaded ones, sticking up from the edge that you would take your either on all of the components, which would be rare if you were testing the circuit board, or at a critical sort of attachment points that you'd press a second copy of the circuit board down on top of and usually clamp in place. And then you would have some wiring hooked up sort of to your harness that would apply power or signals that would sort of test your circuit in place. It's a way of doing testing that doesn't require you to make any connections other than sort of put this in a jig, clamp it in place, and a bunch of pins sort of connect to specific places and do your testing. For this board, for example, maybe there would be, a pin that would connect to power in, ground, RF in, RF out, and maybe a couple measurement points to like check bias and things. Sort of clamp, assemble all the components, clamp this in place, and hit run on my external tester, which could be built on an Arduino. That would say like apply power, apply minus 90 dBm signal, measure output power, apply minus 80 dBm, measure output power, and do like an automated test, see if it all worked, and light up a little green LED or red LED. So the whole testing process goal is then you pop it in, you hit go. Green light, good. Green light, good. Red light, bad, and so on, just to automate process that way. That's what sort of bed of nails testing is. You can use test points for that as well, for sure. But you can also do them, for sort of like the hobbyist process for sort of manually testing things. A couple more things you might want to think about. Trace width. We looked a little bit at that trace width calculator and maximum current limits due to trace width. You might also, I've certainly have done this as I've been prototyping things, on a 2-layer board especially, where all of your traces are exposed, you can use a chisel or screwdriver to cut the traces just by scraping the copper off of a layer, which can be a useful thing to do. If you've messed up the routing of something or gotten the pin out wrong, you can scratch the copper off and or bodge wires between things, certainly as we saw earlier that I did. That is certainly possible. Labeling, I mentioned I encourage you to put a version number on all of your PCBs. I have so many of these little frickin' circuit boards, and if they didn't have version numbers to keep me honest, they all have like a lot of minor differences. So version numbers, do it. You'll be grateful later. Do you need mounting holes on your device? So like, how is your device going to mount into a case or in front of something? This has 3 large mounting holes. This one has, you can see, has 3 large mounting holes here. I try and keep my mounting holes on that same 0.1 inch grid as everything else, just to make it a little bit easier to like define an attachment point for them later. This one I did not succeed because it's kind of cramped on here. But this one is like, these is like 3.6 inches, and this way is like 4.1 inches or something. So I can, in Fusion, make a case for it without too much trouble. And then, like, as you are manufacturing these things for your hobbyist use, thinking about, do you want to give yourself options to put additional components on the board? So, for example, just to keep abusing this poor little PCB, this is contains a little buck converter. This is the little moving light control board that I've been working on that I think I mentioned last week. It contains a little buck controller current driver for LEDs. One of the key components of which is, I think I have an assembled one here somewhere, but of course my table is so covered in PCBs that it's going to be impossible to find. That's all right. This component here is an inductor, which is a key part of the buck converter circuitry, and I wasn't sure when I assembled it. Oh, here we go. Let me show you this one. That's a big fat, through-hole inductor capable of carrying 1 amp of current. But I also was like, well, I might step it down. Like having a smaller, cheaper part that's surface mount but could only do half an amp might be something I'm more interested in. So you can see on the unpopulated board here, I actually have 2 different footprints on top of each other. I have these 2 through-hole pads for that big through-hole inductor we saw a moment ago, and those 2 are sized for a different part that's a surface mount inductor that does less current. So you don't have to commit yourself to populating every position on your circuit board. You might give yourself some options if you wanted to play around with things later. This is a board I was testing specifically out the programming, so I've added like this microcontroller, a crystal, and this header, and I haven't populated anything else on here because that's not what I'm doing with it. So as you're thinking about testing these things, think about like, what might you want to assemble to do a basic test of. One thing I wish I had given myself the option of was a more direct way. This is a DMX decoder chip on it. I wish I had a way of injecting DMX signal directly into this microcontroller without going through this IC, but I didn't add the test points that I would sort of need to do that. So thinking about what signals you might want to inject to test your device as a prototype without having to populate everything can be a really useful thing. I think that is it. I think that is the curriculum. That is the things that are on the schedule for tonight. What have I missed? What questions do you have? And Palmer, thank you for slowing me down a little bit there. I was feeling the pressure of time, but I'm happy to be here. This is by at 20 minutes the longest night. So those of you who are still here are true heroes and heroines of your respective places for sticking it out this far. I hope it's interesting, and I hope you will consider making a PCB for things. It really, like, it can seem a little scary at first, but I think I showed this PCB off last week. This is a really simple device, but a really useful one. And it's so easy and cheap to get these things manufactured. Like, if you needed, even if you need, I said this at the museum where I work, a couple months before we shut some things down, was like, I had to make a display adapter for something, to take in some signals and do some processing and splurt them out. I was like, how many of these am I gonna need to replace? Is there one? If there's one, I'm gonna probably just make a thing by hand on perfboard and solder it together, and it's fine. If there's two, I might do it by hand. If there's three, I'm gonna make a circuit board, and I'm gonna like make this a thing that I can build 5 or 10 of and make it repeatable. And that really is, like, in many ways, for like anything that's even a little bit complex, the tipping point for me is like, how many of these I gotta make? I gotta make one? Sure, I'll do it by hand, or prototype something by hand for sure. Like, if I was ever going to, make a more formal version of this, yeah, sure, I'll do the prototype by hand, maybe do the second prototype by hand, and maybe have to order a couple different, iterations of the PCB. But, once you're starting to look at, like, I need like 10 little boards that have, like, a transistor and a resistor and a terminal block to hook up to an LED and a jumper to select a thing, right? If you need 10 of those, just order a PCB. It'll be here in a week for $20. The time you save in the manufacturing is so, I think, and it's your money, not mine, I think is worth the money, and it's really fun. Nate's on the West Coast. Oh yeah, thank you, Nate. Thank you for sticking it out here over in West Coast land. I have fun. I'm originally a West Coast boy myself, and so I'm envious of your time zone and your lack of humidity. Chris says making PCBs are fun. I want to get more made after updating. Yeah, making mistakes is just part of PCB manufacturing. Actually, I would really recommend, and this is maybe more for myself than everybody else, but like the number of times that I've clicked order on a PCB and then like 30 minutes later be like, ooh, it'd be really great if it had this test point or this feature, or like you get so fixated on like how the thing is gonna work. It's sometimes hard to like think about like what am I gonna use it for as a prototype, so I don't have to do another version. Or you just order another version, like you just get another revision made, and keep things rolling. Yeah, they're really easy. They're really fun. They're pretty forgiving. You could use a PCB to make like an off-board version of the Arduino, like we talked about a couple weeks ago, with a chip and an oscillator and an LED. That's essentially what I've done. What I've done here. That is a little ATmega 328 chip. That's our ISP header. That's our crystal. That's a little tiny, basically an Arduino on a board that's doing other things. Really pretty cheap, really pretty easy, and a lot of fun. Like it's really satisfying to get a bag in the mail and be like, I made this. How super cool. This is another design. Like for a long time, I've just used the Arduino Pro Mini in sockets as like a basic form factor. Here's like 2 Pro Minis, 6 FETs, a little prototyping area just with some random holes, voltage regulator, that same DMX circuitry that I know and love now so much. All very good. Chris, I need switches like you made for a project instead of header pins. Yeah, what Chris is referencing is a really common way of selecting options on your Tommy cam on your parts, and I'll just demonstrate this quickly, and then I will finish this crawler and call it a night. Let's say, for example, I'm going to use I'll use this little module here. A really common way of like selecting what connections are made or not made, if you have a little selection of headers here, is to use these little 0.1 inch header jumpers, which basically just connect 2 things next to them. So you might say, like, if this is 2 digital pins, if this one is grounded, do one thing. If the one next to it is grounded, do the other thing. In the center, say the center pin is ground, I could put a header on there to select one option, or put a header on here to select another option. Or you could have just the presence or absence of the header be that option selection. But that's a 0.1 inch header is the keyword to search for there. They come in a bunch of box of big ones for pretty cheap. Thanks, Lee, turning into pumpkins. I think I must do the same because this has been a heck of a night. Thank you for hanging out with me. Thank you for all of your time. I hope this was helpful. We'll be back next week at 7 p.m. Central Time. As always, Here's all the business. If you have questions, comments, issues, concerns, you can leave them in the comments of this video. You can also find information on my website, jeff.glass. Or for pressing questions, I always take questions at Twitter, jefffersglass. Find me there. Next week's topic, I think, is going to be this wireless modules. We'll see. I mean, no promises. Hopefully it'll be less than 3 hours and 22 minutes, but we'll see. Keep taking care of each other out there. Keep staying safe, keep washing your hands, keep doing good in your communities, keep reaching out to people who need help. I feel very, very fortunate and privileged to take the time to do this on Sunday nights. It's the place of strength that's giving me strength to go out and do good things in the world to these days, and I hope it is for you too. You are all great. Keep bashing, and I will see you next time.